Okay, there we go.
All right.
No. As simple as that, and then you can just flip it maybe close to your mouth. Yeah, yeah, that works.
Get my chest rumble.
Fair.
Hola, 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 hola. Micro rojo, ok. Hola, hola. Hola, hola. Hola, hola.
Hey, everyone. Go ahead and get day 4 started. Thank you, everyone, for the past 3 days. It's been awesome so far. So on to day 4. So today we're going to hear first from Russell Stoneback, who's here in person to talk about Pysat. And then we'll hear from Eric Grimes, who will be a virtual presenter to talk about PySPEDAS. Same slide as yesterday, basically. Just remember to keep on putting questions that are science or presentation specific in the proper channel for the project. And all tech questions go to tech questions and so forth. And yeah, you know the drill with the cards now. So some people have been asking about how to save their work that they've been doing on HelioCloud. This is also pinned in general. Sandy went and wrote this up for us yesterday. Thanks, Sandy. But yeah, basically just in HelioCloud, go to new launcher, terminal, get you a Linux terminal, zip all the files there with this command here, where myfiles.zip is whatever you want to name your archive. And when that finishes, it might take a minute. You can go back to the HelioCloud file browser right side, and then your home directory is the myfiles.zip or whatever you chose to call it. Select it and right-click download to your local machine. And then once you're home or back at your hotel, you can go and unpack all of that and continue working. You'll need to make sure to install Jupyter and so forth to use locally. And make sure to download all of that content by next Wednesday, end of day Eastern Daylight Time. Yeah, that's what it is. At that point, they're going to be spinning down HelioCloud to stop spending a bunch of money on it when it's not being used. You can also, if you just want to get the notebooks and content itself, from what people have been presenting, it's on the GitHub repo for the summer school, which is at the link shown in the slides. And I'll make sure to send all this out in an email as a follow-up to the summer school, but so you know. And then just miscellaneous. Again, always check general for a link. If you're looking for one, it's probably pinned somewhere therein. If you're using social media, keep using that hashtag. And if you want to, again, connect with us, make sure to go to our website, heliopython.org. On our contact page is a bunch of different information for that. As extra note today, when those back doors are closed, if you could use the opening at the side, that would be great. If you feel the need to go out the back doors, do it quietly. Don't let the door slam. And yeah, keep holding on to those badges and internet connection info at the end of the day and leave us your index cards. Russell, you're up.
Good afternoon, everyone. My name is Russell Stoneback, and I'm here to talk to you today about the Python Satellite Data Analysis Toolkit, or Pysat for short. So Pysat has a pretty general focus. Though satellite is in the name and in the abbreviation, really it's not satellite specific whatsoever. With Pysat, we're trying to build an entire workflow around data in general. So it's not necessarily space science specific or even science specific, but data specific. So because of this kind of general focus that we have that's larger than just space science itself, Pysat has applied and been accepted as part of the NumFocus family. So NumFocus hosts a variety of packages in Science Python, including things like Xarray, NumPy, SciPy, Pandas, Matplotlib, pretty much most of the Science Python foundation and infrastructure that we can build science packages on top of, and also includes, of course, SumPy and AstroPy. So because Pysat has a pretty broad focus, I thought it would be informative to, rather than start directly with demos, but to start with a bit of a story time, really, to try to explain kind of what the approach that Pysat is taking to get this generality in data analysis. All right. So Pysat's story actually starts with something that I've called the light guitar. So this is an invention that actually caused me to go to physics graduate school. So what you can see here is it looks like a guitar. It's made out of metal, but it works effectively like an acoustic guitar. So an acoustic guitar is usually made out of wood, right? It's got strings. You apply vibrations to the strings, which goes to the body, which causes the body to vibrate and produces sound waves and music. So this works pretty much the same way, but the body is made out of metal. Instead of vibrations in the metal, what we do is we apply high frequency electricity to it in the frequency range of about 20 megahertz to 20 gigahertz, or the same physical size as sound waves, but here's electromagnetic waves. So the resonant surface here is actually high frequency electricity. So it's the resonances, electromagnetic resonances within this cavity that operate effectively just like an acoustic guitar. So the light guitar makes music we can't hear using colors we can't see. So I kind of had a project that had this idea. I wanted to get the music out, but because one, we don't hear electromagnetic waves, and two, the time scale is all different. Everything with the light guitar, because the frequencies are much higher, turns out the time response is much shorter. So if on a normal acoustic guitar, if you played a note and it lasted, say, 3 seconds, on this light guitar, it lasts 3 millionths of a second. It's just the difference in wave speeds between light and sound. So anyway, I needed a way to understand and hear what the outputs of this light guitar are. Being a scientist, of course, I can't just bring up a light guitar and not show at least a little data. So I just wanted to show some measurements here. In this lower corner, these are measurements of an acoustic guitar from the late 70s. So on this bottom panel here, the guitar, which normally has a sound hole, is covered up. And what you do is you get one main body resonance. And then with a sound hole open, you actually get a lower resonance, which is called the Helmholtz resonance. It provides a low frequency response for the acoustic guitar. Up here, I have some measurements from the light guitar. The green is without a sound hole. And you can see you get a similar type of body resonance. And then with the opening or the aperture in the light guitar, it produces an additional resonance, the Helmholtz resonance, which produces this extra lower frequency resonance. And you can just see kind of through comparison that it looks just like the acoustic guitar. And acousticians also commonly use electric circuit elements to help describe some acoustic behaviors. Now, officially, this is what they would call a lumped element approximation, so it only applies at long wavelengths. But for the purposes of this talk, I'm just showing it as a reference that there is an association between electromagnetic waves and acoustic waves. The more official description is that both fields satisfy the wave equation and have the same boundary conditions, so you get the same types of solutions at the same sizes. Now, the reason why this is associated with Pysat is I needed to write software so I could take those measurements and apply them in a productive way and get music out. So the way I did this is I turned to GarageBand, right? If some of you aren't aware, is a recording studio software that comes with Macintoshes for a while now. So what I did is I wrote a plugin for GarageBand. So normally, if I would write science software, it would be personal. I just write the software, execute it myself. I interact directly with the software. But with something like GarageBand, users interact with GarageBand, and then GarageBand tells plugins what to do. So what I have here, this is a light guitar plugin that I wrote, and it works with GarageBand. So what it technically does is it impulse convolution with the impulse of the light guitar. So what you can do is take some input music, either a live guitar, something recorded in GarageBand. You load up the plugin, GarageBand routes the music through the plugin does its job, hands the data back to GarageBand, and then GarageBand continues on and does whatever it is that the user wants. So the reason I'm bringing this up here is that music has a recording engineers have a very versatile workflow that has developed over 80 years or so, where they've been able to record all different types of music with all kinds of different processing and things like this, and a workflow that's able to accommodate all of those things in a consistent way. So with my experience here writing this plugin, I kind of seeded the ideas of a way we could approach data analysis and science in a way that kind of mirrored that recording engineering experience. Okay, so starts out music recording in the 20s up to about the late 50s. The technology limited the recording media itself to only supporting 1 or 2 audio tracks at a time. So if a band wanted to record a song, you have to get the entire band into the studio at once. The engineers would set up maybe 1 or 2 microphones, play the song as it is, and that's what gets recorded, and that becomes a song. So if anybody messes up during that time, right, you got to redo the whole recording, and everybody has to be present at the same time. So for space science, this is kind of analogous to the way some missions are done now. We have to get a whole bunch of scientists together at once. Everybody's working on, say, 1 satellite at a time with a variety of instruments, but it takes a lot of work all at the same time to get things going. As time went on, though, technology improved, and around the late mid-50s, multi-track recording came out. So the first multi-track recorder, I believe, was sold to Les Paul in 1955. And somewhere around the 60s or so, it started percolating into other studios and onward. And once you shift into multi-track recording, it opens up a whole different thing. You can have, say, a musician in Los Angeles record a guitar part, and then 2 months later, maybe you have somebody in New York add piano or vocals, or you can have a singer do their own background vocals and things like that, overdubs. It just opened up a whole thing. You don't have to have the whole, everybody together at once, all working in concert, perfect for things to work out. You could break up jobs into different times, different people, all kinds of things like that. So the workflow that they developed during this transition was primarily hardware based. So this is a recording console over here, which was actually used for recording Pink Floyd's Dark Side of the Moon. So this is a late 60s console, I think. Dark Side of the Moon was released in the early 70s. And by about the early 70s, the overall hardware workflow for recording engineers has been pretty much solidified because it just works. So if you compared, say, the hardware or the flow of this old music console versus something that's manufactured recently, it's the same workflow. So this one's all digital and things like that, but it's the same. And here's a screenshot from Apple's Logic, which is a fancier version of GarageBand, and it implements the same workflow and software. So there's really a lot of versatility that's been provided from this audio recording chain. And I'm trying to recreate the same type of things for Pysat. Because in the history of space science, we've had a few satellites going at a time with many scientists per satellite. Though we do have some constellation missions going now, they are a few satellites. But now with some of the corporations out there, there are literally tens of thousands of satellites out there active right now. And hopefully not too long, we'll be able to get some science instruments on those as new ones go up. So in the future here, we might actually have tens of thousands of data sources going at the same time. And we need a workflow that can actually support this many instruments. If we do them one by one, I mean, there's just not enough postdocs to handle that many instruments at once, right? So, so this is what Pysat is trying to enable for a small team, 1 to few people, to be able to manage, say, like an entire orchestra, where each instrument here is like a different data source in space science or something else, and bring all these different sources together in a way that's actually practical and feasible and workable, and then produce results with it. Okay. All right. So I have talked about the recording workflow. So I just, as a scientist, just give you a little demo. I do have a cover of 7 Nation Army up on the internet if you want to check that out. So you can search for 7 Nation Army. Mr. Kiwi is the name. That actually refers to my cat right there. That's the cover. And then I have this alongside my Pysat manuscript that was in JGR Space Sciences, because it's like a different variation. The music cover, right, is the direct application of the recording workflow to music, and Pysat is the application of that music recording workflow, but to science data. All right. So if you check out this manuscript, I build up Pysat, but also mention and describe how we can build instrument independent analysis functions. So we can do things like I can write, say, a general seasonal analysis tool that does a seasonal binning. It'll work for any instrument and it'll work for any person. So we can build tools that will work for any data source. We can validate them independently, and then lots of people can use them. So if we start as a community using some of these developed tools, it lowers the workload on scientists. And for the community, somebody's using that tool, then you kind of know what work has already gone into it, if it's been unit tested, if it's been validated. So now it provides an opportunity as a community that we can kind of band together. So if somebody comes along and says, I don't believe your results for certain reasons, if other people have also been using that tool, then they have direct experience with it. They know how well it works or not, and then they can stand up, as a community and say, no, these tools are good. The data is right. We're not doing anything nefarious. We can publish, open workflow science papers and things like that, and hopefully, for certain communities, provide them with a bit more robust view of what scientists do and the quality of our analysis. Okay, so a technical summary, it's up there on the top, but Pysat builds upon X-ray and PYSPEDAS, create a versatile data workflow, abstracting away the challenges of file and data handling, enabling robust instrument independent scientific data analysis through a consistent, easy to use interface. So it's a bit of a mouthful, but that's the plan, is that we built things that you can attack data in general ways, but apply it to specific data sets. Data comes in all kinds of different flavors and forms and standards and dimensionalities. So to get some kind of consistency, we had to encapsulate the data and all those things within an object. Now, I know there are many programmers here, but just in case, and for people in the wider world listening, an object-oriented interface is kind of providing, making it like a box. And inside the box, there's data and other things, but you don't directly go into the box, because on the outside of the box are buttons. And the button might say download or load or give me data or do this. And you just interact with the buttons on the outside, and the buttons in the box know how to successfully translate that to the stuff inside and then spit out what it is that you want. So by taking a step back from directly interacting with the data, it gives you a layer of abstraction that makes it easier to use and makes it easier to translate whatever it is that you've done to a different data set with very little effort whatsoever. So the analog here for the Pysat instrument is for a particular data set. The analog here is like a single audio track or recording from a single musician. It supports both PYSPEDAS or X-ray. So if your data set is just one-dimensional, then it's going to go into PYSPEDAS, because PYSPEDAS is really good at that stuff. PYSPEDAS does not scale as well to higher dimensional data, so that's why X-rays come along. So we also support X-ray as well. So, and you can actually interact with both of them in the same way, even though the underlying data format is different. So that's pretty powerful. We don't just store data, we also store metadata, right? So PYSPEDAS itself doesn't store metadata, X-ray does. But for consistency, the instrument object itself always handles the metadata. So independent of what your data is, there's a consistent way to access the information about your data. There's all kinds of options for loading. You can load by day or file or ranges of days. There's support for iterating through your data set like you would any kind of list or something else like that in Python. There's on-the-fly orbit break determinations or iteration. This is more like a satellite feature, but satellites going around can have a different orbit period depending on which way you want to call an orbit. So say if it's you want an orbit that goes from 0 to 24 local time, that's going to be one amount of time for the satellite to go around. However, if you wanted, say, more longitudinal based analysis, that orbit period is different because, of course, the Earth is rotating as the satellite goes around. So to get back to the same longitude, it's going to take a different period. Also, things like solar local time might be a little consistent, but if you, so my experience is in ionospheric electrodynamics, primarily in the equatorial region. A lot of things with plasma motion and things like that. So the plasma is really heavily influenced by the magnetic field. And if you have a magnetic local time, that period is not consistent from orbit to orbit, just the way the magnetic local time definition is. So without some kind of on-the-fly orbit break iteration or determination, there's no way to get a consistent orbit unless somebody else calculated it already for you. But my general experience is, well, one person wants in an orbit is not what somebody else wants in an orbit, which is different than what the satellite operators are gonna say, perhaps give you as this is your orbit. And science is really all about customization, when we don't just load data and then stick it together and be like, we're done. I mean, sometimes, but frequently there's custom analysis. Either you need to add a particular calculation that you want to do. Maybe you come up with your own. Maybe you need to put data together, do some operations. So it can't be too confining. Otherwise, we're not going to be able to actually do science. It has to, the instrument object has to make it possible for people to do whatever it is they want, kind of whenever and almost however. So as part of that, there's support for custom keywords, so you can pass custom options to underlying data sets. And you can add your own functions that get applied to things. And all these features together, produce what I call instrument independence. So you can write software that works on data, and you don't have to specify the data ahead of time until somebody comes along and says, I want you to do that with the ACE data. And then you can do that. And then you can also apply the same function to some other spacecraft, satellite, ground-based radar, model, whatever it happens to be. Of course, some of those things might have different analysis things. So there's more than one analysis type thing to do, but there you go. And there's more. To build on that, and then we also have the constellation object. So the analog here is like the recording console. Recording consoles are made up of many individual audio tracks. Each audio channel is just like the other one. So all the knobs and things like that that go down this thing, each channel, they're all the same. And like the ones I showed before, they had 24 tracks. So you could have 24 different individual music recordings. But for somebody to hear that, you have to combine all those tracks together down to 2 for something like stereo. So the console itself brings all those channels together, and then it has some features so you can actually determine how those individual tracks are put together, summed together. So that's what the kind of constellation object is. It's one, you can have a whole group of different instruments together. So it could be different satellites, different models, different space weather indices, whatever it happens to be. And then from there, now we're also building features on top to help you work with a variety of data. So the constellation object is not as well developed yet as the instrument, but right now it is instrument compatible. So if you write something for an instrument object, you can go in and drop a constellation object in there and it should work. So that's why it's instrument compatible. You can also operate at the constellation level, say load all the data at once, download all the different data at once, clean all the data at once, process it all at once, things like that. And then of course, data and space science and other things, there's always challenges, right? If you have multiple data sets together, the likelihood that all those data sets always have data at the same times and the same ranges, things like that is going to be virtually zero. So we're developing functions and stuff within the constellation object so that it'll automatically determine based on the loaded data that you have, what's the common time range and things like that. And you can just operate on those common times or not. It's about having lots of versatility and more features to come. Like I say, we're still working on this, but it's more of the focus has been on the instrument object itself, getting that really where we want it, and then building upon it with the constellation. Okay, so the Pysat data flow. This is kind of like the heartbeat of Pysat. This is why I started talking about the audio workflow, because this is the implementation of my understanding of the audio workflow as applied to data science. All right, so I know there's a lot of stuff up here, but I'm gonna go through it all for you. So it's gonna start up here with the user. A user is gonna come along somewhere, they're gonna load up Python, they're gonna load up Pysat, and they're gonna say, I wanna work with some data. So the first thing you're gonna do for that is you have to instantiate the instrument object, which is you're telling Pysat, I want the object, here's the data that I wanna work with. So that's this call up here. And primarily there are 4 dimensions that you can select the data set. The primary one is platform. So if you're dealing with satellites, this might be, say, CNOS, that was the name of a satellite, or DMSP, or ACE, or anything like that. So platform is the main thing. And the name would typically be like an instrument within that satellite. Some instruments will produce more than one data set, or you might have a type of data set that's available for multiple providers, or for like a space weather index for, say, DST. Yes, DST is a good one. DST will release a preliminary value kind of in a short time, right? But they take time for processing and checking and things like that before they release the official one, which comes out later. So some people might want DST as soon as possible. So they're going to want, say, maybe the real time or the temporary ones. Other folks might be, I don't need stuff now, but I want to make sure all the numbers are exactly, as good as they're going to get. So things like tag allow you to select within an instrument different types of data sets. And then we also have inst ID here. So like if there's a constellation of 6 identical spacecraft, you can pick out, this is the one spacecraft I want to work with this object. So there's also support for clean levels. So the data that is put out or released publicly includes good data, so-so data, bad data, all kinds of stuff. And the people that are in that mission and the scientists producing those data sets, at least by modern standards, are supposed to put cleaning flags or other things like that to help scientists determine what data is good. But that might not always be true for all data sets, especially if they're older. But what it is right now, if people want to work with a particular spacecraft or data set, is kind of incumbent on the scientists to find the data and then find the publications covering the data. Hopefully those publications talk about how you determine what's clean data and what's not. And if you're able to sort that all out as a scientist, then it's up to you to write your own code and implement those cleaning options correctly. So what we have here is with every data set, there's already a built-in cleaning function that's provided as part of the plugin support. And then, but it's here for the user. They can select, I want no cleaning, or I just want the good data, or I want good data plus so-so data, or things like that. So there are a few options there for the clean level. I mentioned there's an orbit iterator. I'll be talking about this more, but you can provide some of that information here. There's some data padding options. I will be talking about more of that later. You can put that in here. And I mentioned also there's all kinds of custom functionality and things like that you can apply to the instrument object, and you can also add them in instantiation. So we've got an instrument object now, say user pick something, and then after you've defined it, normally you're going to want to load data, right? So let's assume that the user issues the inst.load command. So for all instruments, if you want to load data, it's .load. It's the same for any data set because you're interacting with the instrument object, not the data itself, right? So the user applies the load command. They tell Pysat, these are the days I want to load. So Pysat will pass that into itself and say, hey, inst.files, user wants some data. I need you to give me a list of files that correspond with what the user asked for. So for all these features, Pysat actually needs to understand what files are on your machine. Okay, so that's part of it. So it'll tell Pysat, give me a list of files. It'll do that. And then it'll pass it on to a load function. So for each data set, there's going to have to be a developer that comes along that writes a plugin to support that data set. Just like my Light Guitar plugin worked for GarageBand, Pysat is like GarageBand, and each data set is going to be like a plugin. So at least one developer out there in the world is going to have to come along for every data set and write a load function to load the data. And then after it gets loaded, internally, Pysat is going to take that data from the load function and then pass it to what we call a pre-process function. So this is also provided by the plugin author. So, it's nothing, so it's provided by the plugin author. And it's just there for sometimes when you load a data, you need to do something first, whatever that happens to be. So like one example, since I was on the CNOS program and I was on the ion velocity meter team, or IVM, for part of the mission, the IVM was operating at a cadence of 2 hertz, right? So I had an output sample every half a second. But for data quality and other reasons, partway through the mission, we decided, it would probably be better if we slowed that down a little bit down to 1 hertz. That way the data quality would be better. So we did that. But it can actually be a challenge in some functions if you're doing, say, a Fourier or a wavelet type analysis, if your sample rate changes on you and you don't know. So like for CNOS IVM, in this pre-process, at least at one point, I just had a little routine in there that looked at the date and then recorded the sample rate as either 1 hertz or 2 hertz. And then later on, as I had my functions that deal with it, I could just go and check on that attribute that I set from the pre-process thing. Anyway. And then it goes to the clean function. So the clean function that I brought before is not a Pysat supplied clean function. It's here for the developer of the plugin, the person who's most familiar with the data, to write the clean function. So hopefully the actual instrument team. So they can put in the code that actually defines what is clean data, or what's dusty data. That's what we call dusty, which is good, and some that's so-so. Or you've got dirty, where even some of the data is bad. Or you can have none, where this just doesn't get called whatsoever. So for every data set, somebody's gonna have to come along and produce these three functions to provide that particular support and translate it into Pysat. And then once it goes through that system, then it's gonna be going through this whole Pysat thing over here. I'm gonna be talking about these more in detail later. I don't just wanna keep it all flowcharts, but there's all kinds of time-based calculations and other things where you may actually need not just today's data, but you may need some of tomorrow's data, maybe some of yesterday's data. Say you're gonna do a standard deviation calculation on density or something like that. If you wanted to do that as a centered calculation at the beginning of a day, you're gonna have to wait until you have enough samples, right? Until you can actually fill up that 30-second buffer. With Pysat, it makes it so internally, it'll take the day that you've loaded, it'll add the previous day, it'll run your calculation, and then it'll take the previous data off. So then when it comes out, you just get the day that you want, but your time-based calculation is valid everywhere. So there's a variety of features that we have built on top of this data cache that's built here. Pysat also has this nano kernel. So I mentioned there's custom functionality. So you can write your own methods, your own functions to be attached to the instrument object. So whenever a user comes along and says load, these functions automatically get applied to the data before it ever comes out of the instrument box. So this is important because it actually means that the data as it is on disk and the data that comes out from the instrument object don't have to be the same. So it could be, you can actually have multiple, some data sets will distribute files by orbit, but maybe the user wants to load by day. We can do something like that. I'll be talking about that more. And then after it goes through all of this stuff, it will go through this orbit iterator, which is basically just the general data paginator. So you can write some condition. I want to iterate on the data whenever X happens. Pysat will go through and find those things, and it'll automatically chunk the data that way. So you can just write a normal for loop, like for inst and other inst, and each time that loop goes, it'll just have that chunk of data that you're looking for. So the abstraction by having this whole process built into the instrument itself means that the data on disk and the data that come out doesn't have to be the same. And as a user, you get to tell it exactly how you want all that stuff to happen. All right. So Pysat itself is not just Pysat, it's an entire ecosystem. Like with GarageBand, while GarageBand has a lot of functionality in and of itself, it's not complete without all the different plugins that different developers have produced out there. So right, all kinds of distortion or reverb or all kinds of other things that make music interesting, right? You need support for those. So Pysat is the main interface for users, but it in and of itself doesn't have data support for emissions because it would make Pysat itself too big. So Pysat itself is the user interface, and all these packages over here, these four with all the arrows pointing towards Pysat, these are data source plugins. All right. So we've so far pretty much grouped them by either the type of data that you want, like Pysat space weather. So Pysat space weather has a variety of indices. So space weather indices. So it has, excuse me, like F10.7 radio flux, DST index, KP, AP, things like that. So a variety of kind of simple index data. Pysat Madrigal over here interfaces with NSF, National Science Foundation's Open Madrigal database. So we have access here to actually all the different, all the data sets that are offered by NSF. CDAC is, or Pysat CDAC. CDAC is for the Cosmic Data and Analysis Archive Center. So Pysat CDAC provides access to the data sets that are hosted and distributed by CDAC, in particular, like the Cosmic 1 constellation with all the GPS radio occultation profiles. So we have support for all the profiles that they have, like the atmospheric profiles, ionospheric profiles. There's like seven or eight different data products, data sets that are in Cosmic 1 GPS for their profiles. We also have some support for Cosmic 2 that's coming, things like that. Up here on the top is Pysat NASA. So Pysat NASA is a bunch of modules and support to interact with NASA's SPDF's CETA web. So one of the earlier presentations, like Happy and things like talked about the different data sources. NASA's also, this Pysat NASA is all set up to get data from CETA web. So right now we have all the different modules for generalized support for all the things that Pysat needs to do. If you or anybody else wants to add your a NASA instrument, you just have to go and effectively say, here's on CETA web where it is, write a clean function, and then you can include it in Pysat NASA and share that data with everyone. So you don't really have to start at zero. Each of these modules has a variety of functions to support interacting with that particular data set. Pysat models provide support for model data. So right now we have support for like TiGCM, SAMI2, also support for DynaS, which is a general database model thing that I've been working on. So here we plan to include more and more model data. So not just satellite data. Pysat CDF. So CDF is NASA's preferred data format.
Yeah, there's a question in the chat. Who defines clean in clean level? Is it data product specific, or the user needs to have a good understanding of the data and the cleaning required for that data product?
So the primary responsibility there would be on the developer and their knowledge of the data set and translating the 4 or the 3 levels that we have into parameters. So the 3 levels that users can, or the 4 levels that users can put in are clean, clean, dusty, dirty, or none. So clean is for good data. It's on the developer to determine what is good data and put those parameters in there. The dusty, it kind of just, going from things, it's mostly clean, but some of the data might be so-so or not sure. So it'd still be on the developer to determine what those levels are and translate that appropriately. Dirty would be very limited cleaning. So the developer there should only take out the stuff that they absolutely know is just completely unworkable. And then the 4th level is none. And to make sure that there is no cleaning, if a user does that, the clean function just doesn't even get called. So then you just get the data as it is on disk. Thanks. Pysat CDF provides support for loading CDF files. It's a combination I actually wrote. It's so high level, it's in Python, but it invokes a bunch of Fortran functions that are then coupled to the actual NASA CDF-C code. So it's a bit of a Frankenstein, and it sounds like it would be a mess, but it works very well. So Pysat CDF is actually pretty performant at loading. Right now, it's focused on lower dimensionality data, but I'm hoping to be able to extend this to higher. All right, so these are all the different sources that you can have right now, or you can develop your own. Of course, these are the public ones that the Pysat team has developed and put out there. Over here on the left side are more uses. So Pysat missions. So science, well, for some groups, science starts when a mission's already up and data starts to flow. But to actually get a mission, right, there needs to be a team that has an idea and then is able to write a proposal that gets funded and on and on. But to get a proposal funded, at least from NASA, you have to show ahead of time that your mission is likely to succeed scientifically. So that typically means you have to come up with an orbit, right? You have to run that orbit through models to get out the actual physical parameters that you're going to get. Then you typically need to feed those parameters through instrument models and things like that to estimate performance and make plots and all kinds of stuff like that. So Pysat missions is really coupling Pysat with a lot of external packages to make that happen. So different models like the International Reference Ionosphere or the HWM, the Horizontal Wind Model, or MSIS, which provides neutral densities and things like that, composition, whatever it happens to be. Pysat seasons, this is one of those instrument independent analysis functions I was talking about. It does bin averages for you. So I'm sure everybody in this room has seen some paper that like does an average over longitude and local time or some kind of equivalent. And you've got, what they did is they made a little bin, put all the different data in there, and they just did an average. So Pysat seasons is set up to do those types of things for any data set that's supported by Pysat. Pysat Komodo, so this is a link between Pysat package and Komodo. So Komodo is going to be talked about tomorrow. Yeah, all right. So they'll tell you about that, but Komodo is like a little higher level where they're like, don't worry about the data, just tell us what you want and we're going to make it happen. So the idea with Pysat Komodo is Pysat's all about the data. So it's just loading data via Pysat and then passing that over to Komodo, and then good things happen. Pysat tutorials, we've got some demo codes and stuff. And then Pysat incubator is where some code is that's just not quite release ready for whatever reason. Oh, I forgot the stuff on the right. So Pysat is also meant to be built upon. So one of the packages I will be talking about tomorrow is OMMBV or OMV. This is some magnetic basis vector stuff. It's an independent package. It can function completely well on its own, but it's also intended to be provide basis vectors for ionospheric electrodynamics and things like that. So it's kind of intended for that information to be coupled with satellite or other data sets. So OMV uses Pysat as a submodule in there to make a very general coupling that people can use. And Pysat has also been used as a foundational instrument processing software for both the NASA ICON Explorer mission, as well as the NOAA NSPO Cosmic 2 constellation. So running at both Berkeley and at CDAC, the Pysat's running at both those places. And then I built the ion velocity meter processing software on top of Pysat. So that makes the IVM processing software a little bit more general than normal because it's not explicitly tied directly to the form files. It's got Pysat as an intermediate layer to actually help it handle all those things. And Pysat actually creates the files that are publicly distributed by these missions. So Pysat's pretty fundamental for the IVM for both these things. So that means there's also been a lot of work and review and other things that had to go into Pysat to get it on these missions and through the whole process. So if you use Pysat, you can benefit from all the work the team has done to make sure everything is robust and logged and all kinds of good stuff. There we go. Pysat's also finishing up some funding that came through the Naval Research Lab as part of a DARPA project, Defense Advanced Research Project Agency. So they had this overarching project called C, which is Space Environment Exploitation, I think. And NRL was participating as part of developing a next generation space weather model. And Pysat is part of the team there, and Pysat is actually one of the foundational packages to bring all the different data sets and models and things together needed for that program all together in once and put it together and make it useful. So this isn't a flow chart specific to that program. It's just a general thing that if you have a variety of indices, a variety of data sets, and a variety of models, and you want to get some kind of outcome out of it, you can use Pysat to bring all those things together much more easy than without Pysat. Some of it can all be in Pysat, and you can also, download it from a variety of cloud services, using different models. And then you can also couple it with external processes that have nothing to do with Pysat really, but may be needed. So as part of this, we had to do a lot of work to operationalize Pysat. So in code terms, that means like adding logging, tons of unit tests, make sure that everything, deprecation warnings when we move on, things like that. So we really spent a lot of time on type of finishing work to just make sure everything's really robust and as well as user friendly. So I just thought I'd show just one example. This one is an example kind of from Pysat missions. So this is a neutral wind instrument that I invented. It was recently awarded a patent at the end of 2020. And speaking about satellite instrumentation in other countries can be a little dicey. So all these figures actually come from the published patent that are online. So that's why everything's black and white and not color. They're not up to color yet. What I did here is like the main thrust is this one, these kind of panels over here, is that I used Pysat missions to satellite an orbit that I needed. So in this case, it was going to be a CubeSat mission launched from the International Space Station. So I went to the NORAD site or whatever, and I said, NORAD, give me the 2-line elements for the ISS orbit. And they gave those to me. I turned around with Pysat missions, which is built for this. And I said, hey, I've got some TLEs. I want you to give me orbits. It gave me orbits. And then I took those positions of the orbit and I ran those things through different models. So in this case, the horizontal wind model, the MSIS model to get neutral densities and composition. Not shown here, but also IRI and some other things. So I already had like a ready to go data set of what the satellite's going to be and appropriate parameters for all of that. Then I took those parameters, I coupled it into an instrument simulator that I wrote. It takes those parameters, produces instrument curves. Right, and then I wrote a separate routine that takes instrument curves and does geophysical fitting. So I was just showing that, hey, all of that works. But because I did Pysat, I built this all on Pysat. It gave me a whole infrastructure to keep bring all these things together in a way that was really easy to do and allowed me to focus the majority of my time on how do I make this, new instrument as good as possible. So anyway, so this is so some early fitting, but this is the ISS orbit. You can see the neutral composition gets a little funny at times, but that's when it's at 100% anyway. So things get a little confused. Once you actually get some range and some better densities, it's all right. There's a little bit of bias that I introduced in the composition by trying to make the temperature a little bit more robust against noise. So you can see on this side where the signal density is high, there's a little bias in the temperature, but in this area here, it's actually correcting for that bias, which is the thing that sends the composition off. So it's not about the details so much of the instrument, but if you're an instrumentation person, you have to be able to get funding to continue to doing that, and to get funding, then you need to prove the stuff ahead of time that you're doing is actually working. Over here is the theoretical numerical modeling I did of the instrument, and here's some actual experimental results. So this instrument is called SANS, and it is, as far as I know, scheduled to be on this NASA cousin rocket, which is in collaboration with Sweden, I believe, and it might even end up on the upcoming ESA Daedalus mission. So I'm not a part of that anymore, but I wish them all the best. All right, so supported data sets. So right now, it's the data that's up is the data that me and the other people on the Pysat team have been using for their own kind of personal scientific analysis. We're up to about 80 plus data sets now. That includes a variety like their multiple DST, their multiple F-107, things like that. We include all the instrumentation from the NASA ICON mission, which is current right now. So if you're into that kind of equatorial ionosphere stuff, it's a good place to be. Space weather indices, we've got a variety of models already. Things like CNOFS, DMSP, the Defense Meteorological Satellite Program. So there's been a long running constellation, the DMSP, Hickamarca Radar Observatory, right? So that's located in Peru. Again, equatorial ionosphere stuff. GNSS TEC, the cosmic constellations. We have our first community pool, which is actually adding support for GUVI. So that's already up. And support for gold is coming. This is not all of them, right? You can tell that's not 80. But if I put all 80 up, you wouldn't be able to read anything. So I just thought I'd throw some out at you. All right, so I've been trying to present Pysat as a package that you can build all of your science analysis and other things on, which is, I'm assuming, very important to you as a scientist and important to your career. So as part of that, the thing that's really important is a lot of documentation. So if you're going to choose to use Pysat, I just want to let you know, we've already spent a lot of time and we'll be continuing to spend time on making sure it's all documented and, so you can actually refer to it like you would any kind of documentation from MATLAB or IDL or something like that. And I would like, and Pysat is intended to have not just the instruments that the Pysat team adds, but the instruments and data sets that the whole community can add. So we've also made sure to have a lot of documentation on how you add a new instrument or make a data set plugin, right? So it gives you everything that you have to do, describes the things that you can do, recommends things, stuff like that. And if you want to use Pysat, we also have a very in-depth tutorial online too. This is all on Read the Docs. So if you go to the main Pysat page, github.com/Pysat/Pysat, you click on the RTD icon, it'll bring you to here. So we try to take you through all the things that you need to know to do it independently. We also have a healthy API, and as wherever possible, we try to do all the good stuff. So we've got warning boxes, we've got example boxes, we've got note boxes. So we've tried to make sure that the documentation looks good, not just effective, but also hopefully looks good, things like that. And if you want to use a particular data set, you're going to most likely want documentation on what that is too. So this is an example from Pysat NASA, and here it's listing right now all the main missions. This is actually from the last version, but it's like CNOFS. We have multiple instruments on the CNOFS spacecraft that are supported. I've got multiple instruments from DE2, the Dynamics Explorer 2 mission. We've got all the ICON instruments, things from the space station, the floating point measurement unit, things from Omni, Gold, etc. Time saver. The list continues to expand. And of course, we've got documentation on how to use Pysat and applications. So this is an example from Pysat Seasons package. That's that generalized bin averaging thing. And we've got examples here of how to use it with Cosmic and some other IVM instruments. So it's 1D examples and ND examples, and you can see if you go through it that they're the same, which is nice. Also, you know, supporting packages. This is something from OMS. It includes results. So there we go. All right, so that's the end of story time, and then I'm going to be moving into demos. Demo time. But I thought, any questions before I move into demos? Okay, I'm not seeing any. Julie, if any come up on Slack, of course, please. All right. Okay, so let's go to the demo. 319. Okay. That. Okay. So just a quick reminder. So this is the Helio Cloud. I'm sure everybody here is familiar with it. I go into the summer school directory at the top level, Pysat tutorial, and then we're going to start here with this first one, ACE. All right. So I'm going to start out, of course, we're going to import things. And first thing is going to do, this is the first time I've imported Pysat and Helio Cloud. So one of the first things Pysat's going to do is, hi there. And then it's going to tell you got to do something. So way back, if you remember when I was going through the whole process flow, I said Pysat needs to know about your files, right? It needs to be able to know that so I can iterate and do all those other cool things that, or I think are cool things that I can do. So Pysat wants to know where those files are. So it generally is going to ask you, hey, we need to know a place to put data if you tell us that, if you ask us to download it or anything like that, and a place to look at it. And it will actually support multiple directories, but just for this example, we're just going to leave it at one. All right. So this is what the second cell is going to do. It's just going to assign a directory for that data DIRs. So I'm going to be using it's Pysat .params. So it's kind of like RC params from matplotlib, but it's not exactly the same, but it's just a central location for Pysat or users to store information. So we're going to say data DIRs, and we're going to assign a directory that's here on Helio Cloud. So it's going to be under shared Pysat demo. And then I have got an if else there because I have like 13 demos up here, and I just wanted people to be able to start at any one rather than have to go through an order. There we go. And as I've said before, Pysat's like GarageBand. All the data sets are like plugins. So we need to tell Pysat, hey, I've got some plugins and I want you to be able to use them. You only have to do this once per installation, but this is a new install, right? So I'm going to start with an example from Pysat Space Weather, since that is typically simpler data. So I'm going to go ahead, all the different data sets or instrument plugins under Pysat Space Weather or other packages are under under .instruments. So we can just pass in this module here to pysat.utils.registry.register by module, and it'll go through that module and it'll register all those different instruments within Pysat. And now the kind of the meat. We're going to instantiate an instrument object here. So I'm going to call it ACE. ACE equals Pysat.instrument, right? Instrument object. The platform here is for ACE, the Advanced Composition Experiment. We're going to be looking at data from the SWEEPM instrument. And in this case, I want to look at historic data. You might be wondering, well, how do I know about all these different tags or inst IDs? Or even what is ACE or SWEEPM? So Python has got a built-in help function. And whenever you instantiate an object, we always put the support stuff under .inst module. So if you want to know about a particular data set, do help ace.inst module, and you'll get this nice printout. The thing, so it starts out, lets you know the platform, lets you know the name, but it also defines the tags for you. So in this case, we're using the historic tags. So this is historic data from SWPC or the Space Weather Prediction Center. Alternately, you may not want the historic data. You may want real-time data. And this one, the description is real-time data from Space Weather Prediction Center, right? So SWPC offers data in multiple formats, and that's what we've done. Each of the different things that SWPC offers, we've provided support for. And for ACE, they're just 3 categories are enough. We don't need inst IDs, so it's just left as nothing. It's got an example. It lets you know if there's any warnings with the data set. As you can see, a clean function is defined in here. And there's a load function that's also defined. There can be custom options within the load function. There's not question.
Actually, it's a yellow card. I don't know if people have questions they might want to ask right now, but I just noticed a lot of people are still waiting for HelioCloud to spin up.
Oh,
So we may want to vamp for a moment.
I'm sorry. Yeah.
Not your fault.
All right. Well, then I'll. But I'm running. Okay, well, I will try to not progress too much and I'll just keep talking about this particular one and hopefully it's able to catch up. So I mentioned before there's support for custom keywords or custom options for data sets. If any were defined, they would be showing up here. So you don't have to, just automatically know that some data sets have some options. It's all going to be listed here in the help to let you know exactly what this particular plugin offers and what kind of options that you can do. Okay, people may still be loading, but I'm gonna click this next one. So you may also want information about the object that you're actually working with, right? So you can just do a print on ACE, that's the name of the general object. So first is gonna just give you the basic stuff. Hey, this is an instrument object, right? Here's the platform you told us, here's the name, here's the tag, here's the inst ID. And I was just talking about custom processing and custom keywords. If any of that stuff is defined, then it's going to be here in this block. And you can see there's a variety of different things that happen behind the scenes, but Pysat needs to know about files, so there needs to be a routine to identify what those files are. You can pass options there. There can be options to load, options to the pre-process. Pysat supports downloading through analysis. So there's also download routines that are required for all the data sets. So you don't have to know where to go and get them. You don't have to worry about organizing. You can just tell Pysat to download those for you. There's also options for the remote files, listing remote files. So some of y'all may have worked on an active mission before, right? So it's the data set's not complete, but data comes out in chunks or things like that, and you may not always know when one's going to come out. So we have routines that'll look at the files that you have on your system. It'll go to the remote server, find and identify all the files on the remote server. And if there's a new file or a file that you don't have, it'll download those, but not the ones that you already have. So you can just periodically, if you're working on a current mission, just invoke this download updated files method, and it'll just keep your local data set completely up to date. So when Pysat goes through to parse those things, it'll look at date and version, revision and cycle keywords and other words that you can define yourself. And in this case, there are 0 custom functions applied. You can see there's all kinds of different functions here that are listed as having support for keywords. So I will show an example later, but Pysat knows which ones will go where. So you just have to give the keyword that you want at instantiation, and Pysat will make sure it goes to the right place. Okay. So local file statistics. I said Pysat has to know about files, and in this case, I've already downloaded some data. So there's 31 days of data already on the system, and it spans this date range. And loaded data statistics, nothing has been loaded yet, so there's nothing there. So normally, if you're starting with Pysat, you would, in a data set, you'd want to download data. So for all instruments, please don't run this. So for all instruments, you can just invoke .download, and then you put in the time range that you want. It'll go to the server. It'll download that data for you as long as it exists. To make sure we don't hurt the servers with everybody trying to download at once, I went ahead and downloaded all the data plus a little extra for all the examples already onto HelioCloud. And all the data is in that shared Pysat demo folder. And the way I got all that data on HelioCloud was just, I logged on earlier, just ran all these commands. And then, I told the supporting folks with NASA, hey, here's my data. And then, it's in the shared folder, and now we're going to get to use it. So if you're at home or you're trying this not live, you feel free to run this, but please don't do it now so we don't, hurt the servers. Okay, so we've instantiated an object. we've looked at it. We've looked for options. We know a little bit more about it because at the beginning it talks about what ACE is, a little bit what SWEEPM is. Anyway, now we want to load it. So I'm going to do one which effectively no options. Normally you're going to tell Pysat, this is the day I want, these are the range of days, this is the file, etc. But this is a space weather index, the files are small. So if you don't provide any time range, you just do a .load, Pysat's going to load everything for you. There is this use header equals true keyword in there, and that's just an option that loads any top level file metadata into a particular place in the instrument object. So we had one behavior in Pysat, and now we're moving to a new one. So if you don't have this use header keyword, it's just going to give you a warning. Hey, meta now contains a class for storing global metadata. Default attachment of global attributes to the instrument will be deprecated. Set use header equal to true to make this go away. So as I was saying, we spent a lot of work on making it a robust package to build upon. And as part of that, if people are going to build on your software, when things change, you have to let people know and provide time for them to, actually make the change. But to limit the number of red warning boxes during the demo, I've gone ahead and put the use header equal to the true in all the different load statements. So now all the data is loaded, it's within the instrument object. It'd be great to make some plots. So why don't we just plot everything? So that's what this code is. Let me go ahead and run it. It's going to do its thing for a second. So just to start out, I provided a start date. So the data on the system is from July 1st to July 31st. And I could have plotted all that, but I just thought I'd show that you can down select from all the loaded data just interactively. So I defined two dates, July 5th, July 27th. So the instrument object has got a property or an attribute .variables. So if you do .variables, it'll give you a list of all the variables that are in the object, and that works if it's pandas or X-ray. So we need to have some of these attributes like this because pandas and X-ray don't have the same commands. They just, some things they do, but some things they don't. And if we didn't try to have like some kind of common baseline, then it would be more difficult to work with Pysat depending on the data set. So the data is not hidden. It's all actually just, I'll show you in a second. But so this is a list of variables, and we're just going to iterate over that list. Going to make a figure for each variable that we come across. I'm going to pull out the units and title from the metadata information. And then here, this is the ACE object, right? So ACE, I want you to give me data between my two dates. And I want you to give me the data for the variable that I want. And that's going to return a pandas series, because in this case, it's a low dimensionality data set, right? Just 1D stuff. So it's loaded in a pandas object. So it's going to pop out a series because it's actually storing a frame underneath. And so the dot plot is actually just doing the pandas plot. Pysat doesn't explicitly provide any plotting. That's for other folks. And then I pass in the title, the label. I added an X label, height layout, and for some reason I'm saving these. So you can see this first one popped out, MJD. This is the mean Julian day. Julian day is just one of those, happens to be one of those kind of awkward times. Seconds of the day, status. And in this case, for this part, there are no changes in status. Yeah, all right. And now we're actually getting into like more science stuff. So ACE measures things about the solar and wind proton density. We got a plot. Remember this label, this is all coming from the metadata. It also has solar and wind bulk speed and solar and wind temperature. All right. So in this example here, even though it's for ACE and SWEEPM data, there's only one thing in this demo that's actually particular to ACE and SWEEPM. Only one thing. Got to go all the way up. This is the only part of this demo that's specific to a particular data set. So you can put in a different data set that Pysat supports, and all of this should work, even if it's a higher dimensionality object. All right. Might naturally bring up a question, well, what other data sets does Pysat support? Well, you can actually use Pysat to tell you. It'll tell you the things that you've already registered. Let me type. Pysat utils, then I'm going to hit tab here. Ooh. I'm going to use tab to bring up the introspection thing, and we can do display available instruments. Like that. Boom. So these are all the different data sets that are now in Pysat because we registered Pysat space weather. Now there are in reality even more data sets in different packages, but since we didn't register those yet, they're not going to show up. So this is all the stuff that would work right now out of the box in this example. As we go through these demos, I'm going to register more instruments packages with Pysat, and then after that, then you could come here and do that with this one too. So you can see we list the platform. So we've got multiple things for ACE. Also got just some general ones, SW for space weather, DST, F107, KP, all right? Different ones can have different tags. So we list the different tags here and the inst IDs. So in general, it could be not every single instrument in constellation has all the same data products. Sometimes they're different, right? So it can be instrument ID and tag specific and can vary. In this case, there are no inst IDs that are required because this is a simpler data sets, which is why I started here. And then just a general description, right? Real-time data from SWIFT-C, historic data from SWIFT-C, historic DST data collated by and maintained by NOAA and CI, right? So things like that. Just general things to help you get situated on what you need or what you want. So in this loop, right, there's nothing really specific to ACE or any other data set. I just want to bring this one up here real fast. So all the metadata is stored under .meta. It's actually stored right now in a data frame under .meta.data. So it's all available, and if you actually want to mess with it directly, you're welcome to do so. And different files have different metadata standards, right? One group might call units one thing, and a different group might call units a different thing. What I've got here is some generalized, the way I've written this one makes them more generalized for changes, but it's not actually for file metadata standard changes, right? Because the data on disk and the data that comes out of Pysat do not have to be the same. And as part of that translation, it's built into Pysat to convert the metadata as in the file into the metadata standard within Pysat, so it's always consistent. Okay? The thing is, users may not always want the default metadata system that we have. They may want to do their own metadata, and that's totally fine. So when you instantiate the object, you can actually tell Pysat, this is the way I want you to label and other things metadata. So this, scrolling. So this stuff here is just a bit of safety, because this is like an interactive demo. People can come and put in different data sets and put in your own options. And I wanted to make sure it worked no matter what. So if you wanted to go in and stick in a new labels thing and tell Pysat, I want you to call metadata different things than what you normally do, this code will still work. If you don't do that, then you don't actually have to have this general thing. You could just do units, not newits, units. Where's this one? Name probably. Hold on. There we go. So as long as you didn't go into the instantiation thing way at the top and tell it to do something, this will work for any of the data sets as well, independent if it comes from NASA, CDAC, or anywhere else, right? Even though all those places have different metadata standards. So one of the questions that I would really like to get out of everybody's lexicon and our scientific field is, if you talk to somebody, be like, oh, I want to use your data. Normally people would follow up with, well, how do I download that data? You can just download it with Pysat, so no reason to ask that anymore. People might also ask, what file format is that data? Who cares? With Pysat, it doesn't matter. It's not specific to any file format. You just tell Pysat load the data. It doesn't matter if it's CDF, NetCDF, ASCII, whatever. Or people might ask, well, what kind of metadata do you have? Things like that. It doesn't matter again anymore. If you're going to switch to Pysat and using Pysat, the data is always going to come out in the same standard way, the Pysat way. And it's also set up that you could tell Pysat, I want you to do that a different way, and it'll work. All that translation stuff will sort itself out. So it's pretty nice. You don't have to ask where the data comes from, how do I load the data, what the format is, what the metadata. You just don't have to worry about it anymore. Yeah. All right, so I think that's all the points that I wanted for this intro demo. So I'm gonna, any questions?
Several. Yeah, I was going to say several in the chat.
Perfect. All right.
Do you want me to read them to you or do you want to
Oh,
look?
I guess I can go to Slack. Warren Reds. Let's see. Is the historic sweep data a compilation of the past real time, or is it a more cleaned up version of the data? So what we're downloading there for the sweep is we're downloading from the source, and they've labeled it historic, and it's the data as been provided by the data provider. Offhand, I don't exactly remember what processing was applied to sweep. Oh, please help. So somebody tried to help ace.inst module and it didn't work the way they want. So thank you for bringing that up. I forgot to mention this at the beginning. So what version is running right now on Helio Cloud for Pysat is a release candidate 0 for 3.0.2. So if you're at home or running locally, what you're going to want to do is go to test PyPy and download Pysat there, and it'll be 3.0.2 RC1. But that'll be good. So the inst module is one of the things that was added in 3.0.2 as a always present object. And the previous Pysat, sometimes it was there, sometimes it wasn't, and that introduced some issues. So how are sub-instruments broken down inside the instrument object? For example, the PSPISOIS instrument suite has epi high and epi low, and epi high has multiple telescopes. EPIM on ACE is broken down into 2 LEMs and 2 LEFs instruments. The appropriate way to break down would be to, the most appropriate breakdown is going to be developed by the determined by the developer. So if multiple things need to be combined, then you could do that internally, or if it's best to keep them separate, then most likely I would say you have the platform and then the instrument, and that's what the tag and the inst ID options are for. So generally, the first one to go to would be tag. If there's multiple data sets that you want to support and allow people to go through, is you just have different tags. And then if that's not enough, or there's other things, then you can also use the inst ID. So there you actually have like 4 degrees of freedom to separate all the different data sets that a user may need. But at the end of the day, it's really up to the developer and their experience with the data set and what they think is most appropriate. So Pysat doesn't enforce any of that on you. It's up to the developer to say, this is what we do. Next one. After running the load command, is all the data loaded into memory? Yes, so the load command I did here with the ace.load, that's going to bring up the warning. All of the data is going to be loaded into data frame, and all of that's just that .data. So we don't restrict .data. So if somebody wants to come along and just completely nuke that and put their own thing there, Pysat's not going to stop them. So that's not what we're trying to do. If you pick too large a data set, will I run into memory issues? Yes, absolutely. So suppose a person has like 1,000 PyGCM files on their system, and they load up PyGCM object and they just do .load with no date range or file range. It will continue to load data until your computer says no. We don't have any checks for making sure you have enough memory or things like that. And that might even be a variant of like the general halting problem or something like that. Maybe, I don't know. But no, we don't try to do any of that. So normally I don't really do .load, but I just thought for this most basic example, and because the data was small, that it would be good to just show that that was a possibility. All right, I think that's all the ones I've seen.
There's one more that just came.
Maybe I need to scroll. Is there functionality to harmonize multiple data products from different instruments, yet to the same time system, region of interest, etc.? Yes, that stuff is being developed, and that's in the constellation object. I don't actually have any demos today on the constellation object. I thought it'd be good just to focus on perhaps the lower level stuff. And while the constellation object absolutely does work and is useful and is being used within our own group for research and stuff like that, it's just not as complete yet as the instrument object. So you're welcome to use it. It is productive. Just know that there are more changes will be coming to the constellation than the instrument object. So. Okay, cool. Thanks for the questions. All right, so let's move on to the next demo. 01. So this is going to be ACE SIS. And there's going to be a slight twist with this one, but you're going to see as I go through it that it's very similar to the last one. Actually, all of these are going to start out in very similar ways. I want to just keep emphasizing how Pysat is really data set independent, and it's the same process no matter what data you're looking with. So again, we're going to start by importing stuff, still working with space weather. So I've copied the second cell in all the different demos. So you may have recalled them the first time when I did that first cell, Pysat popped up and said, hi there, you need to do stuff, right? Well, we did that stuff. So now when I import it again, it's not going to complain at us. And the second one here is going to determine that there's already a Pysat directory has already been set, so it's not going to change it. So I did that so that way if people download this locally and run it on their own system, it doesn't mess with their own settings. I don't want to mess with that. And then I've got the registry statement again here. It's not actually going to do anything because everything's already been registered. But again, I wanted these to be independent demos. So now we're going to instantiate this data set. So now the last one, it was ACE for the platform and then sweep them for the name. And in this case, we're just going to put in SIS. That's going to get us a different data set. And it turns out just SIS like the variety of ACE products, all of them I think have a historic and a real-time option. I'm just picking the historic. And it's the same thing. You can do help with on the inst module, and it'll bring up the thing for ACE SIS, right? ACE is Advanced Composition Explorer. S is a Solar Isotope Spectrometer. So different measurements, same type of platform. Again, it's got warnings, so I'll let you know, hey, the real-time data actually has a changing period of time. So, so some of the features in Pysat may not work so well with the real-time data just because of the aspects of the data. That is not a typical outcome, but sometimes things happen. All right, so I'm going to define here a custom function. I want to be able to operate on the ACE data. I just don't want to load it and use it as it is. I want to load it and do stuff with it. So I'm going to make this function. I'm just going to go ahead and hit the button first. I'm going to calculate the ratio. It's not going to be anything difficult. It's a demo, but ACE SIS. After we load the data, you'll see it's got a couple different energy channels where it measures, proton stuff. So some people might actually look at the ratio of those, the abundances at an energy to maybe do some curve fitting to see what the underlying energy distribution or something. I just wanted to come up with something. So this function here is going to calculate the ratio of the 30 MeV flux divided by the 10 MeV flux for the protons. And then it's going to add the ratio in place, and I'm going to call it ratio 3010. So the first thing that in my definition is this inst, INST, that's normal R shorthand for Pysat instrument. So the one requirement for these type of custom functions for Pysat is that the first input is the instrument object. So we pass in the whole object. So that way, all of the data, all the functionality, all of that is always there no matter like where you are. But for memory and other things, we don't copy. It's moved in place as it were, okay? So it's going to be performant. So here I want to calculate the ratio. I just, var1 is the first variable, var2 is the second. Obviously it's going to be a little simpler. Take the ratio right over here. And then to assign the data to the instrument object, I just need to give it a name, the ratio _ 30/10. And that's it. Now that data is in the instrument object. We're good. All the data is already there. But we also need to add metadata, right? Data is good. Data with metadata is even better. It doesn't really help anybody if you calculate something and you don't tell them what it is, right? Now, of course, if it's your personal software, you may know, but with Pysat, it doesn't just have to be personal. You can share it with the whole world. So, all right, I'm going to describe it. It's the ratio of the integrated proton flux. This is like a long name. And then defining the metadata, I'm just going to put it all in a dictionary. So here are the 6 basic default aspects that Pysat tracks for metadata. If you want more or less, you can define that, that's fine. And again, I'm doing it in the most general assignment, so that way if somebody comes along later and changes options with the instrument object above, it'll still work. If you don't tell it to change the metadata, then you can just use units, long name. Most of these are actually pretty close to what the actual textual name is. And then to assign that metadata to the object, all the metadata is stored under .meta. So just like assigning it to .data, you just do .meta, you put in the name that you want, and that's it. And then I return nothing. Return nothing with this because the instrument object is like moved in place type of thing. When you add the data there, you've already added it to the instrument object. You don't have to pass it back to be added. It's been added. It's already done. And then I want to actually attach this function now to the ACE object. So I could have defined this first and attached it in the instantiation, but in practice, my style, I usually, define it, and then I use this .custom attach. So custom, you're going to do what you want. You want to attach, you put the function that you want. You can have, in this case, you don't need it, but you can have arguments and keyword arguments that are defined here. And then when you attach it, you can put those in there too, and they'll get mapped, right? So we already have the ACE SIS data on the HelioClad system, but if you're at home, then you can do the .download, the first day they want, the last day that you want, it'll go to wherever it needs to go, and it'll download that, and it'll put it in that Pysat directory that you told it to. And it'll be all organized. It's going to be organized by platform. Oh, all right, 10 minutes. It's going to be organized by platform name, tag, and inst ID and things like that. So it's going to be already really kind of easily or nicely organized on your system. And you can tell it to organize in a different way too. So we're trying to enable systematic versatility as it is. Okay, so we've already downloaded the data before. I already did that for you, so we don't need to run that. Now we want to load all the data. I've got the use header, just to get the warning away. We could print just to, again, let you give everybody a heads up of what's going on. The first time I did this, there was nothing in this area, but now we've got one thing, custom functions, one apply. And the 0th function is here, and then we print the Python representation. And Python gives you some memory address or something. I don't actually know what that stuff is. But that's what Python gives us. So we're not improving on that. Everything else here is kind of the same. Now I've actually loaded data before I did the print on the object. So it's going to tell you information about the data that you've loaded. We loaded the 1st of July. That's the first day here. It gives you the day of year. It's going to give you the time range of the data that we fully loaded in the object, right? The full month. Number of times, number of variables. It'll start giving you variable names, though in practice, there's usually more variables than we can list nicely. So you get the little ... And then it's going to tell you what the kind of metadata is. So it's got 7 metadata variables, or 7 different types of metadata applied to 7 different variables. And it's going to let you know, in this case, we don't have any higher dimensional data, and we don't have any global attributes in this case. But there we go. Let's go ahead and run this thing too. So it's the same pretty much demo in a way as the last one. I've got the start date, the end date. Rather than all the variables, I'm just going to iterate over 3. I'm just going to define 3. So for var and variables, it'll just iterate over this list. And in the same way, it'll plot the figure. I pull out the units in the title. I tell the ACE object, hey, these are my date range. This is the variable I want to plot, and it's going to pop out a pandas data series. So on that data series, I'm going to hit the plot command, and it's going to pop up. These are already here. So here's the ratio. This is the thing I calculated. All right. Now in this demo, you might go, well, what's the point of all this custom stuff? I could have just applied the function. I could have loaded the data and then just applied the function to the object and called it a day. And that's true. But by having the instrument object itself, like self-processing, you can define all kinds of stuff that you want done to the data. And then you can take that object and give it to another person. You can give it to another analysis routine, anything like that. And maybe an analysis routine needs to load 60 days of data, one at a time, because maybe you have memory requirement restrictions. So without this custom functionality to do something like that, you'd have to crack open that analysis code that goes through all those data and then say, hey, after you load the data, change it by doing this. But that's not a good thing to do because anytime you're cracking open some established piece of code, you know, now you got a new copy and all kinds of other stuff. You break all the unit tests, perhaps, stuff like that. So we pulled that functionality in the instrument object so it's self-processing. So you can hand it off to things and they don't need to know what happens. The Pysat object knows what needs to happen. So somebody defines, these are the things I want you to do, and then it happens automatically in the background. It frees up and it enables all kinds of really cool stuff. And then here's just, you know, here's the 30 MeV flux. Here's the 10 MeV flux. If you want, you can confirm the ratios. So, you know, the last one I showed would work with any data set. This one in general, except for it would work with everything, except that in this case, I've attached a function to it that is ACE SIS specific. But if you're doing a different data set, you can do your own custom function, right? There's no limits here. The only requirement, like I said, is that the instrument object is the first thing that is passed in. Okay, any questions in person before I go to Slack? No, let me go. Is cleaning level equal clean by default? Yes, thank you, Raphael. Yes, absolutely. Clean level is clean by default because as scientists, we want clean stuff by default. So it's like default safe. I used to be an instrumentation guy and I spent a lot of time on the file and even doing RPA, not RPA flags, cleaning flags and things like that in the file. But then quite frequently I would get emails from users who either didn't know it was there or things like that, or even in worst cases, seeing data get into publications that's just not good. So to try to limit that, yes, absolutely, clean level is by default clean. Is it possible to download only a select number of variables from, say, ACE rather than downloading the whole data for the date range of interest? So no, not in Pysat, and that's reflecting my instrumentation experience in making those files. All the variables that I put in those files are there for a reason. Now, maybe not every user needs them, but overall, I just find it's easier and safer just to load everything. All right, but if you are writing your own data plugin module and you only want to enable that for that particular thing, you can absolutely do that because in the load, you can define your own custom keyword, and then within that routine, you can do whatever you want. So not generally, but if that's something that's actually very important to a particular data set or something that you're working with, then you can do it. Yes. On the help, it says
Yeah, please repeat the question before you answer.
Oh, okay. Thank you. So the question was, if you look at the help.module, you look at clean, you're saying that the default is defined as none. Where does it say that? Oh, Pysat.instrument. Okay. Clean level, yeah, okay. Yeah, we're gonna just have to update that because in practice it actually is set to none. I mean, set to clean. So there's some artifacts from my earlier development. So some of these things I defined as none, just that way, because I had checks later on. And if that check got a none, it'd be like, oh, this is not right. Since then, we've improved things so that some of those things just can't happen anymore. And we just haven't fully gone back and cleaned all those out. So yeah, thank you for bringing that up. And I think a clean level is going to be defined on the instrument object itself. So let's see, ACE dot clean level. Clean. So good. While I'm doing attributes, while I'm here, it's also got things like year, day of year, date. Oh, if I spell that right. Date. We can look at AVE, ACE. Here's a list of all the different files we have. In this case, ACE is 1 file per day. That's not always true, but either way, ace.meta. Let me do a print. So if you do a print on the ace.meta, it'll give you, of course, the summary of all the different metadata that's there. This one's also, at the instrument level. You can actually check out the actual metadata yourself. It's just, in this case, a data frame. So ace.meta.data will get you there. See, I got 2 minutes before the break. Yeah. That's, yeah. There's another one. I'll have to look that one up. So not that one. All right. So last minute, any final questions before the break? Let me look at Slack too. Are you interested in expanding Pysat on the instrument developer side by adding common processing function used by multiple teams? For example, for particle instruments, having something standard that calculates velocity moments like density, temperature, etc., to any data that is given in a specified format. So on the Pysat team as itself, we're already pretty loaded up with working on Pysat itself, but everything is set up for users to be able to do whatever they want. So if somebody out there wants to write some of these things, we would love that. And you can make your own module or something and call it Pysat velocity or whatever, make up your own name and things like that. And it can even be brought into the full Pysat thing. So we are completely open for community development. But as most of our focus itself is on Pysat and the direct ecosystem things and making it possible for people to do all those kinds of fun things. Thanks for the question. Please, the recent Pysat version is, so on Helio Cloud, we're running RC 3.0.2 RC0. There we go. On test PyPy, you can get that one as well as 3.0.2 RC1. Most things here will work if you're on the previous release 3.0.1, but like the ins module thing won't, or a couple other things, and more warnings will pop up. If you go to test PyPy, you can get like the same one we're using here. Thanks for bringing that up. Is that it for, I think that's any other questions in person? All right, great. Well, then let's go to break then, huh? Yeah. Thank you.
See you all again in 15 minutes. Whenever you're ready, Russell, go ahead and start again.
Okay. Well, welcome back, everybody. I hope you had a lovely and refreshing break. So we're going to go on through some more of these Pysat demos. So I have, what, 10 left or so, 11. I'm not expecting to get through all of them. So I have some here at the end that are more generalized versions of the things I'm talking about now, where I go through all the specific versions. Oh, let me actually expand this out while I do that. So, right, I've got database demos here near at the beginning, since, hey, data is the attraction, right? But starting from about down here, these are more just generalized, like on the Pysat loading, I'm gonna go through all the different options, things like that. So just in case I don't get through them all, which I'm not expecting. Next up is gonna be the DMSP polar ion drifts. I'm gonna get rid of this. Okay, so I'm going to be using, it's going to be similar in some ways to the previous demos, but I'm going to be using some more established or publicly available code, and I'm going to switch to a different data source plugin. So let me import these things. So you might notice at the bottom, it's import Pysat Madrigal as PyMad, Pysat Mad. So Pysat Madrigal, as a reminder, provides data access to NSF, National Science Foundation from the US, all their different data sets. They're hosted by the Madrigal database. And they've released a bit of open source Python code, which I believe is Open Madrigal or Madrigal Web. But Pysat is coupled with that publicly available code to interact with the NSF data appropriately. Okay? And just like before, we're going to set the Pysat directory. Everybody on Hilo Cloud, it should already be set, so it's not going to mess with it. Again, we've got a new data source plugin. So we're going to register it to make sure Pysat now knows what's going on. That's done. Okay, so a DMSP is the Defense Meteorological Satellite Program. It's been a very long-running constellation that has had a series of ion velocity meters, or IVMs, which is the instrument I spent a lot of time on. DMSP is kind of an older program, so when it first started, there wasn't the same kind of community-based rules or associations. It's a DoD Department of Defense project. So at the beginning, it was just, it was for their needs and their purposes, Air Force and things like that. So they didn't really care. Of course, over time, right, there's more push to get the data out. And just as part of that historical stuff, there's multiple pathways for IVM processing. So other groups popped in at different reasons and did some stuff with the files. So there's more than one DMSP IVM set of files up on Madrigal. In this case, I'm going to be picking out the UTD files. I used to be a physics professor at UTD working on this program, so these are the files that I'm more familiar with, and it's the ones that UTD's actually processed, right, and the instrument team. So just as a general thing, if you can get data from the instrument team, I advise doing that rather than from some other source. And the DMSP is a constellation. It's more of a constellation in time. There are, I think, typically there are multiple spacecraft up at once, but it's like been maybe like 40 years or something like that, where there's been some version of DMSP that's been up at a particular time. So I'm just going to pick out one of these satellites. It's F-15. They're all called F and then some number. So that part's not really important. Going to go ahead and instantiate that. It's done. And just like all the other ones, you can do the help if you want to get a little bit more information, right? It's letting you know it's the IVM, DMSP. It's letting you know what the IVM is. IVM is actually two instruments that are combined by the instrument team into one product. And it's letting you know, hey, it's coming from, right, NSF, Madrigal database, all that kind of good stuff. Here are all the different instrument IDs that are supported, right? Actually, let me go back one for the tags. So there's the UTD files. That's the one we're going to be looking at here. There's also, if you just put in an empty string, that's just the general file, right? That's processed by somebody that's a different institution. And in this case, there's support from DMSP F11 to F18. So the DMSP has been long enough that they've had different generation of instrumentation, I think, and different generations of spacecraft and stuff. So we're just looking at a particular series. Yes, okay. So DMSP is in solar synchronous orbit. So it kind of does a dawn dusk type of thing, right? So it's always trying to look at the dawn dusk line. Its primary mission is actually for weather. Military wants to know kind of at sunset and sunrise what's going on there, because that tends to be more important for remaining areas of weather. Anyway, so it's got a high latitude, high inclination orbit. And in this case, what I want to do with this demo is show you the measurements of IVM over the northern magnetic ionosphere. So we just don't want the southern hemisphere data. And as a demo, to demonstrate, what you can do with some of these custom functions, I'm going to define one here. Oh, let's scroll back up, called cell hemisphere for select hemisphere. And like all the custom functions here, you have to pass in the instrument object as the first thing, but you can also have other stuff. So for this select hemisphere, just as a demo, there's the keyword argument hemi, and it defaults to north, but it'll also accept south. So you can go either direction, as I put in the doc string, right, north or south. And that's just a simple if then else type of thing. So if it's north, we're going to pick all the locations where the magnetic latitude is greater than 0. So this is just using the numpy where function. So right, it evaluates that condition, and it's going to pass back a list of indices, integers, where that condition is true in this instance, in this version right here. So those indices are going to end up in this variable IDX. If it's south, it's the same thing, except the condition is less than 0, less than or equal. And and for good code, you raise an error if somebody puts in something you're not expecting. And then for the selection here, I just use the instrument object, the Pysat instrument object interface, and I just pass in the indices. It knows what to do with them. So for all the variables, it'll do that down selection. So this is going to be a pandas data frame. The DMSP files or IVM files are all 1D data. So you use a data frame whenever possible, because it's easier than X-ray. Nothing against X-ray, it's just X-ray is multidimensional, and that just in general can be a little bit more complicated. So this is a data frame now, and I'm just going to assign that data frame to .data. There was already data in there. I'm just going to reassign it. So there's no restrictions that Pysat puts on what you do with .data. So you can do whatever. In this case, we're just going to down select. Okay, so in this case, I'm going to add multiple custom functions. Most of these are not defined here. So most of these here are actually going to be defined over in Pysat Madrigal. So this first one that gets applied is the select hemisphere. The first one that we attached is the select hemisphere. And whenever we load data, the functions are applied in the order that they're defined, right? What I want to do is actually make a plot of what the ion drifts look like. But as a holdover from just the way DMSP is, the UTD files don't have attitude information. So the DOT and the DMSP spacecraft people, they have attitude, But for whatever reason, they didn't flow it down to our portion of the files or the UTD portion of the files. So if you actually load up the DMSP data and you look at the drifts, it'll say like drifts forward and drifts left. But it's a satellite, right? It could I mean, the different spacecraft have different orbits. And in principle, the spacecraft doesn't always have to be facing forward, though for DMSP, that is part of the mission is, that's what they're supposed to do. The point is I need to add some functions to convert what forward and left means in a way that actually works for plotting. Okay. So I've already developed all these routines and they're part of Pysat Madrigal because if somebody wants to use this data, DMSP, and this is, one of my areas of expertise, I've already written those so I can do my own type of science. So this second one we add here is not quite any of that. I'm just going to do some smoothing of the RAM drifts just to make sure things look nice, right? Make sure the measurements are nice and robust. And in this case, this custom function does have potential keywords applied. So in this case, I'm telling it, hey, it's all defined on that custom function, but different DMSP files will have the same information under a different label. The UTD files under one label, the non-UTD files are under a different label. So that to support the application of this function to both of those, there's a keyword parameter where you just pass in, this is the variable that you're gonna look for the information. So we're just passing that in. It's passed in as a dictionary, so you can do more than one, right? The next, I wanna add unit vectors. So it's gonna add unit vectors in a form that's more useful than forward and left. And then from there, I'm going to actually take those unit vectors and then combine them with the instrument measurements to produce, velocities along those directions. And in the same thing, I'm passing in the same key again, because I want this function to work not just for the UTD files, but for any of the DMSP files. All right, so that's all attached. Normally, you'd have to download the DMSP data, but as I said before, I've already downloaded everything onto the Helio cloud using this command. If you're at home, though, you're going to have to go ahead and run this. And I've also had, in this case, there's a little check just to see if the day of data that we want is actually already on the system. All right. So let's go ahead and load all the data. I mean, not all the data. Let's load some data. The previous examples were space weather indices. They were small files, so I just loaded a month because, why not? In this case, DMSP is not a huge file or anything, but we're just going to load a single day. So in this case, we're going to pass in a date time. So I defined that F date near the top for some reason. And we just pass in that date time under the date keyword. And what's going to happen is Pysat's going to go and identify all the files that correspond to that date. Let's see. Let's do a plus. Well, first, let's look at the data. It's been loaded. Here we go. We've got some data that starts on our day. It goes through the day, right, almost up to the end. You can see it doesn't quite start at the beginning. Well, why is that? So let's look. I have files.files. So the thing is, DMSP files aren't strictly on a daily basis all the time. Some of the distributions are actually on multiple files per day. So in this case, these are mostly chunked. Yeah, that was not the demo I thought it was going to be. All right, sorry about that. Okay, just showing again, if you print all the different stuff that pops out, and now we've got a variety of custom functions applied. So now we've got a variety of things all listed here. And it lets you know what the function is that you put there, right, with the Python representation, which, provides that whatever that is. And it also lets you know, again, what keywords and other things that you applied for that particular function. So you remember what's going on. Statistics and all of that. Okay, so down here, let me just go ahead and hit the button and let that run while I talk. So everything Pysat specific is already done. I defined my custom function, my particular new one. I went out to Pysat Madrigal and said, hey, you've got DMSP stuff. I've attached that. I've loaded the data. All the Pysat stuff is actually completely done. This whole cell, this is just plotting, and it's just matplotlib and stuff. So I'm not, unless there's specific questions, I wasn't going to really cover it. It just goes through the data and plots it all. And then this is what pops out. So you can see got a nice polar dial, magnetic latitude down to about 50. And you can see the multiple passes from DMSP during the day is going across. That's all nice. It's maybe a little small, but there's a classic convection pattern in the polar ionosphere, right? It's supposed to be it's sunward, then anti-sunward across the polar cap. And you can see here it's going like this, and then it starts to turn around at that convection reversal boundary as far as DMSP can see it, right? And it's just the one satellite going across. And there's a variation, right? Because I'm plotting this against magnetic latitude. DMSP is doing its thing kind of fixed in space, but as the Earth rotates, right, the magnetic pole is not aligned with the axis of rotation, right? So as the Earth rotates and that thing moves with respect to DMSP, the actual track and magnetic terms across the polar cap varies from orbit to orbit. So it's good for DMSP and for science in that you get a little bit more measurement range than you would otherwise expect. Okay. So I know this may not be as transparent as the other ones because I'm invoking some custom functions that are already predefined elsewhere. But I just wanted to demonstrate, one, there's already some tools out within Pysat for the data sets that we support, depending. But I'm hoping, to encourage perhaps some other people with their own other data set experience or other calculations that you can also do that. You can make your own package that builds off Pysat, put it in public, get your DOI, write publications on it, and hopefully other people can use it too. So not only help your other scientists, get some work done quicker, maybe more accurately, easy, things like that, and then also gets you credit. So hopefully we can get that kind of system going. Let me look for questions. Does custom attach always need to be called before load, or doesn't matter? It doesn't have to be called before load, but if you attach it after the load, it doesn't get applied until you invoke load again. So the custom functions get applied as part of the loading process. There's nothing stopping you from defining new ones after you load and want to reload. What is the default magnetic coordinate system? You mean, is this a question about the drifts? Oh, can Pysat data be converted to other coordinate systems? Sorry, Rebecca, I didn't see yours at first. So Pysat itself doesn't do anything with coordinates. It's just about general data. So if you are loading a data set that is in a coordinate system that you don't like, you can use the custom functionality to write your own function that invokes a package that does the thing that you need. So, had a window in the way. So like if you wanted to do some kind of coordinate conversion and there's a package out there that did it, you just write a custom function that would take the parameters in the file for the coordinates that you're in and call the package that does the conversion, and then just assign that data to the instrument object. So it's open like this, so that way you can invoke anything that you want. Officially speaking, it's Turing complete. I know that's fancy, but it's Turing complete just because we pass in the instrument object, so it has all the data that you have. And then after that, we don't put any restrictions on what you do. You're free to write your own code, call any package, do anything else. You can completely replace the data that's attached to the object and return it like that. So once you go to these custom functions, it's completely open, So that's the part that's supposed to make it a little bit more versatile. How does one know what coordinate system the data is given in? Well, that would be defined in the metadata as provided by the developer or the data itself. So let's see, let's look for DMSP and see what kind of metadata was put into the file previously. Oh, IVM. So to say that the instrument data is any one coordinate system is maybe not the best way, because there's multiple parameters given in the file. So like right here, we've got altitude, latitude, and longitude. So geodetic altitude, geodetic latitude, geodetic longitude, right? So giving your position with respect to the surface of the Earth. We also, in the file, there's magnetic latitude and magnetic local time. That's all it says, latitude, local time. So the particular model that was used to determine that latitude or local time was not specified in the file. Say you wanted to add quasi-dipole coordinates. So a quasi-dipole is not actually dipole, but the quasi-dipole system is definitely one of the more accurate if you wanted latitude and longitude, and that type of information. So I think that system is available in Apex Pi. So if you want to add the quasi-dipole latitude and things like that, then you could just do a custom function, import Apex Pi, provide the geodetic coordinates to Apex Pi, and it's going to pop out, that system if you want. So yeah, so Pysat itself does not provide any of that functionality in particular. It just provides the framework that you can multiple Python packages towards a data set in a convenient and easy way. Any questions in the physical audience on this demo? Okay. All right. So rather than a more historical data set, I thought it might be good to look at ICON. NASA ICON is Explorer mission that's active right now. It's looking at influences of the neutral atmosphere on the ionosphere. That's kind of one of the larger questions in at least equatorial science in our area. So let's start out importing packages. Let's import Pysat. Again, the data directory thing, it's the same for all of them. In this case, let's go ahead and do Pysat NASA. So I'm going to import Pysat NASA. You don't actually always have to register everything in a package if for some reason you don't want to. You can pull out particular instruments and say, just register this one. So just to let you know that this feature existed, I just did this one slightly different. So here I've also added a simple filter to warnings. So as part of Pysat being robust, we add warnings for a lot of things whenever appropriate, when we think a warning would be needed. So if I didn't put that in there, when I go to load some of this data, it's going to toss up a bunch of metadata warnings that are actually fixed in a pool that's already up on Pysat NASA, but we just didn't, there just wasn't enough time to get that fully in and onto the system by the time of this thing. They're warnings and not errors because it's not going to actually break anything, but it's fixed up on the web, but not quite here. So I just didn't want to have all those warnings get in the way. Okay, so just like all the other ones, we need to instantiate the Pysat instrument object, but this time for icon IVM. So that's icon IVM, and there's actually more than one IVM on icon. So one that normally looks forward and one that looks back. But icon has these modes where the satellite itself slews during this maneuver, so they can look. So these neutral optical instruments can look at northern hemisphere and then southern hemisphere and produce a more complete vector. So during that maneuver, the IVM that's normally in the front gets rotated into the back, and just the way the IVM works, it has to be looking into plasma to make them in situ measurements. So when that happens, A doesn't work. So then there was one that was put on the back that was called B. So during those times, if you want to see ionospheric parameters, you have to look at B. But the overwhelming majority of the time, the instrument that's functioning and looking at the plasma is A. And this one actually just define the clean level just to make sure everybody knows that things are actually getting clean. You can do the help. It's it's specific in this case for icon IVM, but you can see that it's covering the same type of things as as the other instruments. So the load routine here for icon actually does have a custom keyword. In this one, it's keep original names, and by default, it's false. So the icon files were made to support analysis programs that have a global namespace. So multiple instruments would say have a parameter for magnetic local time, or like say MLT for short. if you have a global namespace and you load multiple of these instruments, they each have an MLT, and then they would conflict with each other and overwrite, and it wouldn't be right. So, but Pysat's not in a global namespace. It's in an instrument object. Everything is contained within. So every instrument can have MLT, and then none of them interfere. So what that means in the icon files is there's like all this preamble for each level of the file that's kind of long. And you just don't need it here in Pysat. And I just didn't want to keep typing that stuff all the time. So we have an option here. Just by default, we chop off all that stuff at the beginning that doesn't matter for Pysat. So just to make it easier on users' lives. But we also have the option if somebody wants to retain the actual names as in the file, then you can provide that option. So since I haven't shown that yet, I'll just show it real fast. Well, let me load. I'll show you the variable names, and then I'll enact that thing. We don't need to do this here. I've already downloaded the IVM data, but for people at home or whatever, if you want to do the example, you just define the days to download and define this. In this case, there's more. So the actual download command is here, and that'll work. Pysat also has login. Well, Python itself has a logger package, right? So that way developers can, provide information to users, and users can select how much of that stuff they see directly or pass it off to different files and all kinds of other things. So we've incorporated that logger functionality within Pysat. So normally when you do download, you're not going to see anything, but Pysat is actually providing a bunch of different information. So if you set the level to info, it'll print some of that stuff out. Given the file settings on Hilo Cloud, I don't think I can actually download stuff without causing an error. So I don't think I can run this right now. Now let me do this. If you do this on your own, here, I'll just show you what it looks like when I do it on Hilo Cloud, on my thing, and just do this one download as a demo. All right, so we're going to set the logger to info. I'm going to download the few days, and then at the end, we're going to restore the logger back to the normal thing. So what did I do? Oh, well, first thing is going to tell you where it's going to download data to. It did not set my directory. Oh, that's right. This is what happens when you try to alter demos on the fly. Okay, I've updated my directory. Like I said, if I didn't do that because of the settings, let's try this again. I need to reinstantiate IVM. Okay, well, let's just look at this debugger now. It's already set to info. And when I reinstantiated, it's produced a whole bunch of stuff, right? So Pysat info, Pysat is searching for icon files. So Pysat needs to know about what files it has. So like the first time or things change, you instantiate it, it's going to go, I don't know what files we got. It's going to look. When it finds it, it's going to parse all that information. In this case, it didn't find anything yet because I created a new directory that was empty. So that's good. And then all the Pysat instruments actually have acknowledgements and references defined as part of the plugin. That's super important for science, right? And one of the things, we just pop that out automatically. That way users know that it exists. So let me go down to the download thing. All right, good. So downloading data to the directory, all right, it's the new Pysat demo thing that I set. Letting you know what day it's trying to download data from, and then when it actually works, then I'll tell you, hey, I actually got that data. And then it goes through all the days. We're done. Once it knows it's done downloading, it goes, hey, I've got files. Now let me go see what files I actually got and parse them. So it updates its file list. It starts searching for them. It found 4 for my 4 days. And then it updated the bounds, which is something I'll talk about later. So, and you can see it did not take long to download that data. So it's the same process everywhere. A lot of features within Pysat will have feedback, but most of the time we try to put it into the logger so we just don't fill up your terminal screen. It's intended to be like a daily driver. Do not run this one, but have it as an example in here. I mentioned before for an active mission, new files are going to be coming. So this download updated files here will look at the local system for all the files, it'll go to the remote system, find out all the files, and it'll compare those two lists. And if there's anything more recent on the server or files that for days that you don't have, it'll download all the new stuff for you. So you don't have to kind of, keep worrying or messing with your data. Normally, if you just tell Pysat download between these range of dates, it'll just download that if you have it or not. Okay, let's see if I can undo all the demo damage. Reinstantiate that. We've got data now. Okay. So I'm just going to start with a basic density plot. So instantiating the instrument object here, I don't remember why I did it again. I'm going to load a day of data. Before I showed loading with the date time object, but you can also do year, day of year. So 2020, January 1st. All the information is already loaded, right? And you just use string access to get to the data. So the ion density here by this pops out of the data series. You just hit plot, add title and label. Here you go. But you can see there's a lot going on, right? The satellite goes around 15 times a day. So if you're just trying to look at a daily basis, it's hard to see what's going on with ion density. And orbit to orbit, the density can be different. And when a view like this, it's impossible to see perhaps why things are different. So, just loading by date can be convenient, but for science reasons, it's quite common that you want to look at it in a different way. And at least for ionospheric stuff, one of the ways that works really well is to look at it orbit to orbit, particularly against magnetic local time, right? So plasma is going to be organized primarily like by magnetic local time, right? Sun rises and sets, that's density production and all that. So there's going to be a constant forcing from the sun with respect to local time. So if you look at an orbit with respect to local time, orbit to orbit, the changes there are now going to be changes like due to longitude or latitude or things like that. It's more geophysical variations. But as I was mentioning in the beginning, iterating by orbit can actually be somewhat complicated because orbits aren't constant. Or the data set that you have may not have any orbit information whatsoever. So that'd be maybe up to you to go through and chunk the data appropriately. Or even if it does have an orbit number within the file, it may not be the orbit that you want. Because normally I found that satellite operators might like to use the most northern point or the southern point to chunk the orbits, but that doesn't necessarily have any scientific significance. So normally you're going to want to parse data on something that's relevant to whatever you're looking at. So Pysat's got some features to help make that possible. So I'm going to have to reinstantiate the object here just because I'm going to give it new information. So in this case, I'm going to select January 3rd. This is the day I'm going to load here in a minute. And in this case, I'm going to define a dictionary called orbit info. And I'm going to tell Pysat, this is the way I want you to look at the data and chunk it up as an orbit. So the first one is kind. I'm using a shorthand here, but LT is for local time. So I think you can also put in local time. And then you need to let Pysat know what variable is the time that you want to look at. So in this case, the index is going to be magnetic local time. You can also pass in a period here, orbit period, but I don't need to do that in this case. So I'm going to instantiate the object, also include the orbit info. So it's slightly different than the last one. The instrument object has got this parameter called bounds. So there's multiple ways to iterate over the data, and the beginning and end is going to be set here by the bounds. So in this case, I'm not going to set a beginning bound for reasons that I'm going to explain here in a minute, but I am going to set a final bound, so the next day. I'm going to load data for the date supplied or defined above. And then I'm going to iterate orbit to orbit. So the way to do that is this for loop. So for LIVM, so that's kind of, in my speak, stands for loop IVM. IVM is the main object, instrument object. And because I want to do it over orbits, I do IVM.orbits. And just Python being Python and being cool, even as an independent third-party package developer, you can add support to your package so you can couple into standard Python functionality. So that's why I can use this for loop here, and it's going to do stuff to the data. If I did every single orbit for a couple days, you're going to end up with 30 plots really quickly, and it's going to be hard to see. So I'm just going to check if it's the first orbit of a day. Start out 0 indexed, right? Because Python is a 0 index language. And in this case, now I'm going to create a new figure. I'm going to do a plot of the log of density. And in this case, you can see LIVN. This is just the loop instance of the instrument object. Ion density is the same parameter, right? Just going to do a plot, and that's it. You got to wait for a second for it to do its thing. I forgot to hit the button ahead of time. There we go. So you may have noticed up here, I actually did a load for date. And as a reminder, date was January 3rd. Hey, what's this? First data is from January 2nd. Well, what happened there? Well, what happened there is that orbits, frustratingly, don't care about date boundaries or file boundaries or anything like that, right? Orbits are orbits, and they're completely separated from the rest of those things. But if you're iterating by orbit, generally, I would figure a user wants a complete orbit chunked. So if you ask for the first orbit, Pysat goes, the first orbit, that's a tricky one. So it'll start with the first day of data. It'll break up the orbits, and it'll look at the first one and be, is this orbit complete or not? And if it's not complete, it'll pull up the previous day's data, get the last part of the orbit, and chunk it together to make a full complete orbit for that first day, or the last orbit, or things like that. So these orbits can go across file and date boundaries, but the data you get out of Pysat's continuous, right? So as remember, there's that whole layer of abstraction between the files on the disk and then the data that pops out from Pysat. And that's what this feature is really kind of building on, and using the internal data cache and things like that. So this first orbit starts on January 2nd, near the end of the day, what, 2330, and goes through. And then again, for the next day, on January 4th, what it calls the first orbit, right, actually starts on January 3rd, near the end, and then goes through the beginning of January 4th. Okay, why don't I do, see if, yes, oh, question, yes, please.
Yeah, hi. How do you see what instruments are available in Pysat? Because in Pysat Madrigal and Pysat NASA, you could do like either a help or directionary function on the instrument, like dot instruments. But that doesn't seem to work on Pysat.
So Pysat itself doesn't have any built-in. So what you can do, let me click this button to get a new, here you go. You can do Pysat dot, oh, not comma, dot utils dot display available instruments. And this will do the list of all the instruments that are registered. So when I did this before, we only had registered Pysat space weather. There's only a few things that popped up. Since then, I also registered Pysat and Madrigal. So that's where DMSP, this is where that came from. And that's actually where a bunch of this stuff is going to come from. GNS TEC, that's from Madrigal, Hickamarka. And for Pysat NASA, we just did icon IVM. So that's why there's only currently one. Now you can register everything from Pysat NASA. Register dot. Register by module. I think that's the list. No, that doesn't make sense. All right, that's just a little heads up from gold. That doesn't matter for what we're doing here. And scroll down, let's do this one again. Now you can see there's more instruments. We've got the CNOPS instruments, we've got the IVM, PLP, and VFI, Dynamics Explorer 2 stuff. What's that one? I don't think that was in that last list, but looks like that's in Pysat NASA. All the icon stuff. So the IVM, which is the instrument I have been talking about. Then there's also the extreme ultraviolet, far ultraviolet instrument, MIGHTY, ISS, FPMU. And as a final thing, so that's within code, but within documentation, if you go to github.com/Pysat, /Pysat NASA, that'll take you to the Pysat NASA repo, and the documentation there has got a section for supported instruments, and it lists all of them there. So. Okay. Well, I've got all of this. Why don't I do this? Let me break this for a second. All right, so I'm going to do keep original names. So I talked about chunking off all that stuff we didn't need before, but let's say I want to keep them. It's going to not work. It shouldn't work. That was not where I was supposed to put that. Oh, good, it did break. All right, so the problem now, why did it break? It said, oh, ion density, I don't see that variable there. Of course, we just ran it before and it worked. So let me click the plus, and let's look at what the data is now. So you can see all this stuff before. So the last time I loaded this up, this would have just been altitude. But now it's got this icon underscore L27 underscore thing. So I just wanted to demonstrate how you can define keywords when you instantiate, and then it goes to the right place. See, I didn't have to go, oh, this goes to this particular dataset plugin module thing. I just have to know that the keyword exists, and then I can do it at instantiation, and then it'll get directed where it needs to go. Anyway, let me take that off. Let's run that again. So I showed the demo of just the ion density. What we could also do like a summary, some more stuff. So let's see, I set a date. I do the orbit info just like before, instantiate it in the same way I did before. In this case, I'm going to limit things to just a single day for the iteration. Got a custom function where before I did the np.log10 when I did the plot here to get, you know, the log of the density, given the large variations. But we could also do that as a custom function. So that way it's just part of the data. And even if I hand it off to somebody else for another function, then that log is already there. I attach it. And then from here, it's just matplotlib stuff. It's just plotting. It's the same iteration. So I'll go ahead and run that. And then we're only going to do one orbit. So there's a break you can see right at the end. So it's going to make one plot and stop. If you take that break out, it'll keep doing plots of that orbit for the full day. And if you don't restrict the bounds, then it'll iterate over all available data. And here we go. So now we've got the log of the density is already built in from the custom stuff. And then I just pull out O plus fraction as part of the composition, pull out some velocities, just showing what things look like. And in this plot, you can see it's 0 to 24 local time. So that's the breakdown that we wanted, right? So why don't I, well, why don't I see if I can change the axes on this one and not like I don't know what I'm talking about. I think with matplotlib, nope. Let's try this. So that's going through, it's loading. In this case, I was just hoping to see if I can get the x-axis to show and in local time, just so you can see. Oh, there we go. Oh, that didn't work. It didn't break. One more. Well, maybe I shouldn't demo on the fly. That's why I did this ahead of time. But if you could do that, you could just do loop IVM, the magnetic local time as the X data, and then the other one is the Y data. It'll show you that the time range here actually goes from 0 to 24. And if you take out that if statement in there where I say only plot the first orbit, you'll see orbit to orbit, the data goes from 0 to 24 as long as the data actually exists. So there we go. So there are a few types that are defined right now. There's a local time, which is actually looks for a negative gradient in the parameter, right? Because the local time goes 0 to 24 to 0. So we're looking from that change from 24 to 0. The reason why it's a negative gradient is because, well, yeah, the instrument might not actually make it to 24 MLT on that particular orbit, or it might not go all the way to, restart at 0. There could be data gaps and things like that. So for these general checks, we're looking for gradients. There's one that's there's the polar one. Again, that's looking for like a sign change. So if you get a latitude, it'll break out in the equatorial crossing. We also have support for an orbit number. So if there is an orbit number in your file, you can go ahead and just iterate on that. And makes it, just easy. Also, if you want to come up with your own way, then you can, define the orbit number. You come up with your own calculation, put the orbit number in there, and you can iterate like that. So right now, there's a few ways to iterate by orbit, and it's kind of a little closed off. With upcoming versions, not really going to be changing the code, just going to be exposing more of these parameters within this orbit class to make it easier for people to do orbits that I hadn't quite anticipated ahead of time. Anyway, let me look to Slack. I probably waited too long. Some from Raphael. Just curious, when accessing the icon data in their FTP while in our local VPN network, it doesn't let me see their folders, likely because of some local network firewall. Did you ever have any issues with anything like that in Pysat? Well, my institution now, Stoneris, is my own research lab, so I don't have any of that kind of stuff. Pysat itself doesn't strictly deal with any of that. The download is one of those functions that an instrument developer is supposed to provide. Now, in this case, because it's for icon, it's in Pysat NASA, we've already written a general download routine that should work for any instrument, really. I don't think that one necessarily. I think it's using requests. We used to use something else, but then I think we switched to requests, and it works for me locally. One of the developers, Jeff Cleansing, and Jonathan Smith, are both local at NASA Goddard. It works for them. It works for a developer at NRL. I would say if there is a problem with the actual download thing, then please post an issue on the GitHub page. And if you let us know what the network configuration, whatever it is, then we can work together to sort that out. Yeah. That by orbit part wasn't clear to me. One could start anywhere in the orbit and come back to the same place to complete one orbit, right? Not sure why it has to pull data from a time period that the user didn't want in the first place. Okay, so yeah, so one of the reasons I mentioned before for this, so this is this example here. So the reason why I loaded not January 1st, but January 3rd, and the reason why I did not put a bound, I didn't actually put a bound here. So this is the starting bound, and then the second one is the finishing bound. I left this one unspecified because I wanted to demonstrate how it would go back a file and make a complete orbit. If like, I don't want that to ever happen, you could put the date here, you put your bounds where you're starting. This will just take a second, and it's not going to go back a day. So you can control that, at least on the first and the last orbit. So like the very last orbit you get at the end of the iteration, that one is not going to be complete in general, because you're going to run into the end of your file, and if that's where your bound is, there's nowhere else to go. All right, so here I specified a bounds, right? Start on this day, and now that's exactly where the data starts from on January 3rd. So the reason it does go back is the intent is to make the most complete orbit that we can. Is the intent is to always provide the user with a complete orbit within the confines of the data. In the summary plot example, you don't call IVM load after custom attached. Just curious, does it get automatically applied at LIVM data? So let me scroll down. All right, so you're absolutely correct. I instantiate the object here. I define a function, I add it, and then I don't actually call a load. Well, the load is in here. When I say iterate over orbits, the orbits goes, oh, well, I need data to do that. So internally, it's going to call that load function. I previously started with a load just for a different reason, but in general, you don't need to do that for iteration. It'll automatically do those loads for you. Cool, thank you. Any questions in person? No, okay. When am I done, Julie? I forgot to look.
I believe it's at 5:30 local time.
5:30. Okay, 20 minutes. All right, perfect. Let's see, is there anything else I wanted to say with IBM? Show the custom function and show the orbits. I think that's it. Okay. All right, so all the examples I've done so far have been with pandas. Pandas is just being all 1D. It's a little simpler. X-ray is very capable and great, and we build upon it. So I wanted to show at least one example with the higher dimensionality data. So again, this is coming from ICON. This is going to be the MIghty instrument. So this is a Michelson interferometer thing. So it's going to be measuring some neutral parameters, including temperature and velocity. So it's more complicated. MIghty has 2 instruments, but those 2 instruments are active all the time. So like I said, IBM has 2, but it's only like 1 at a time. But for MIghty, you need both, and then it's a combination of those 2 instruments that produces some of the higher level data products. So in this case, I'm going to build up just 4 different MIghty data sets. So this first one, ICON MIghty, right? This is the vector wind. The MIghty instrument itself is looking for certain emission lines from oxygen, and it's looking at 2. One's a red line and one's a green line for reasons. So this is specifying, vector wind, neutral wind, but coming from the red line. So it's going to have different distribution, local time measurements. There's also the green line. So I'm going to load that one up too. There's also separate data sets that cover the temperature. And both the MIghty instruments, A and B, both have independent temperature measurements. So I'm doing both of those. And it would be just, a bit of a hassle to iterate with all 4 at the same time. So just for this one, I'm just going to put them all into a list. You can do the help on one of them or all of them. It's the same. The same download, all the data is already here, right? So we don't need to do this. But again, all the instruments, the downloading is always the same. You don't have to know. Okay, so here there's not too much Pysat stuff. The Pysat stuff comes right here mostly. I'm going to load the vector wind red data. I'm going to load the vector wind green data using the year, day of year thing. And then from here, we're just basically going to plot. Yes, that's right. We're just going to plot. I put in some limits for the data. I picked a color map, so it's a red-blue thing. Help distinguish positive and negative. Going to be plotted from altitude. That's it. So I'll go ahead and let that run. Going to produce a variety of plots. So here's all the MIghty data for a day. And again, just like with the IVM data, all this stuff is organized by local time. So if you look at a day at a time, it's really kind of hard to see what's going on. It's just part of the nature of the beast. So in this lower example, I do the same thing we were doing before for IVM, but now I'm going to do per orbit on MIghty. In this case, the local time is not quite as simple because the MIghty instruments are remote instruments, or they're looking, each part of the instrument's looking at a slightly different location and slightly different local time. So in this case, I'm trying to create just using that data, I'm going to average it together to produce a simpler, just single parameter for local time. So that's what this add average local solar time little function does. And I'm basically using a lot of X-array functionality here. So this pops out an X-array, and then I'm going to be using the mean, specifying the axis. Here I'm picking out times where the local time is not null. Yeah, so just picking out the good data, and then I'm going to down select all the data that's good, and I'm just going to keep that. Add it, and then from here, that's it for Pysat stuff. Really, everything from here is going to be effectively is just plotting, and I'm going to be using the same orbits type functionality that I did before. Okay, so when I define MIDI here, you can see here's the orbit info. And the index that I'm going to use is average local time. Average local time does not exist in the file. If you load a MIDI file and you look for that, it's not there. It's here. I'm adding it with the custom function. So I just wanted to emphasize that there's a variety of features within Pysat, orbit duration, time series, custom functions, all that stuff. They all actually work together without conflict, and it doesn't require anything on the developer's part for all these things to work. It's all coming for free. So it's going to do the plots over this average solo local time. Here we go. That was fast, huh? My axis is with the numbers all the way down here, so it is 0 to 24. There's different time ranges based on the color and things like that. But you can see you can just see much more in the data by going through by orbit than you could on a daily basis. So it's a pretty powerful tool. It doesn't always have to be local time, but again, just reflecting my own ionospheric experience, that's the one that works best for me. Your data set, of course, and have different ones that would work better for you. But as you can see, right, there's a lot of data gaps. That's nothing against MIDI. That's just the reality of satellite instrumentation. And in particular for MIDI, the lines that they're looking at only work during certain local times because you can only see the emissions. Anyway, and then it's going to be the same thing here for temperature. I'm going to do orbit info again as average local time. MIDI, this is going to be the temperature. My calculation has to be a little different just because of the way the temperature file is. It's a little different. The data is a little different, but it's, again, I'm just doing an average local time by meaning averaging over the data. Then I'm going to iterate over loops. And you may notice that the enumerate and other things like that work with the instat orbits as well. Everything else from down here is just plotting. And I'm only going to show a couple orbits just so I don't, blow up your whole terminal window. But here you go. Here's the temperature distribution. So you can see during the daytime, here you go, daytime, the instrument's able to measure temperatures in the much higher altitudes, and at light, it's at night. It's mostly the lower altitudes. So this is MIDI. I just wanted to show it also works for more complex data than just space weather indices, IBM, or other stuff. Let me scroll down to see if there are Slack questions. I don't see any Slack questions. Any in-person questions? No, all right. It's good we're getting near the end. My voice is gonna go. All right, so that's my data-focused presentations. Here now I'm gonna be switching a little bit to more general, and I'll probably only have time to introduce you to this file writing one, and then probably be working on shutting things down. That's okay though. This is where I wanted to get at minimum. Pysat demo on creating netcdf files. So I focused so far on just loading stuff, but since I've been on instrument and other mission teams, right, some people actually have to make files for everybody to look at. And I can tell you, making files for public distribution is not easy or quick generally. So many meetings on the ICON and other teams were spent on creating the files and the standard. Though to be fair with NASA ICON, so historically NASA only serves files in CDF format. It's their own custom format. I'm not going to go through the history of CDF versus netcdf. But for ICON, they decided to go with netcdf, and CEDAWeb actually approved that. So it was up on the ICON team to come up with what the format was going to be. So what they chose to do was to make a very highly compatible format, which is great. So they surveyed all the different kind of formats and things that were already out there, file standards and whatnot. And to make it the most compatible, they kind of clobbered them all together. The downside of that is there's information in there that can be repeated in multiple times. As a developer, I kind of don't want to always, set the same information at the same time. So there's a whole series of functionality in Pysat for creating netcdf files that will be able to convert the data that you've got into Pysat into whatever you need to do. Whatever it is, maybe you need to rename it, maybe it needs to be special formats, maybe it needs this, maybe it needs that. Got this whole series of functions and opportunities when making files to make that happen. So I wanted to just provide a mechanism to demonstrate some of those. So let me just do stuff like this. Now, Pysat itself doesn't have any data. Originally, old Pysat, the data was in Pysat, but it was too monolithic. So all the data got kicked out into its own packages. But Pysat still needs to be tested, and everything's about data. So we had to create a variety of test instruments. So these cover most of them right here. So I'm going to start when I'm talking is just going to be the simplest instrument, which is the platform is Pysat. Letting you know it's a Pysat thing, and it's all about testing. So that's why it's called testing. And it's just well, maybe I should show you. So we're going to find that. I'm going to load it. Let me open up a thing. IBM, not IBM, inst.data. So it's got UTS, local times, longitude, latitudes, orbit number, all kinds of dummy stuff. These dummies are supposed to be different data types, a string dummy, Unicode dummy, int8 dummy, int16, blah, blah, blah. So we wanted to cover the range of different data and things like that for all kinds of testing, and in particular for writing files. So this cell here, I have a variety of options, and almost all of them right now are commented out. So I'm just going to hit this first. So these are all defined as none. So these are like a safe default. You leave it like this, none of this stuff's going to be enacted. But if you want to try out some of these features that is going to be explained a little bit more down below, you can uncomment these lines, run it again, and then everything should still work. So what is that we're trying to do? Trying to make files. So I just want to demonstrate you can add any kind of global metadata that you want really easy. So in this case, everything got loaded in that meta.header. That was that use header keyword. And then I'm just going to make a new attribute, demo thing, Pysat style. That was my creativity at the time. I didn't have a lot there. And then yes. So now that's assigned. It exists. When I write the file, that's going to get written to the file as a global metadata attribute. So let's see. Oh, what did I do? All right, so the permissions on that shared directory were set so we can't mess with them, right? Because otherwise it'd be shared and people can mess with the stuff. And I forgot to update, I forgot that. So I'm gonna have to go back and go back to that new Pysat demo thing. Let's do this. Let's do extra new. Oh, I forgot. That's the problem. You put in protection sometimes and then they come back to get you. All right, let me comment that out. Extra new Pysat demo, and that worked. Note that directory didn't exist, but when I told Pysat use this thing for a directory, it makes it for you. Okay, so now we've got an area in your own local Helio cloud space where you can write files. So that's a good thing. So now when I run this, it should actually work. And did I get this? Oh, I need to reinstantiate my object with the new settings. Load the data again. Boom. There we go. You see, there is a warning that popped up. I didn't tell Pysat explicitly how I wanted the date time information to be named. It originally started using epoch from NASA because that was the kind of standard that they use. Since Pysat, we're trying to have a little bit more general focus. I'm not sure everybody is going to know what epoch means. And I think strictly epoch is like the start time, not all the time. So we're moving to using just time, but I didn't tell it which one I wanted. So, and we're on that transition where we're going to be just updating the default. So it's letting you know, hey, we're doing defaults, the default is going to change. So if you don't want that to happen, make sure you actually provide a thing. But now if you go to that new Pysat demo directory, I should do that since I'm giving the demo. There should be a file, new Pysat demo, icon, IBM. No, that was extra new. Pysat testing, demo test file. So I did pysat.utils, IO inst to netcdf. So it takes that Pysat instrument object and is going to dump everything relevant to it right to that netcdf4 file for you. And it's going to be within whatever standard that you want. So by default, it's going to be just the Pysat standard, which is like a simplified version of that icon thing. So we still want some compatibility and stuff like that. You don't have to do anything to get that. It's just coming out right out of the gate. So netcdf4, one of the things it requires is underscore capital FILL fill value. There's different people from netcdf4, I think is on the CDAC side, that also have fill val. So there's some standards are going to be looking for this one metadata thing. Other ones are going to be looking for another. Just to be safe, Pysat writes now all of them. Okay. So you can see I also, I gave the file name. There's also this meta translation. So that translates the existing metadata that you have to a different, not so much a different name, but to multiple different names. So it takes like that single fill value to the multiple ones in the file. So that way as a developer, you don't have to copy around all this redundant stuff. You just need the unique information. And then when you write the file, you can just tell it, hey, make this one 3 things or 4 things or whatever. Export and that's all there's some selections. So this is set up that this command should work for any of the settings that are in this cell up here. So you can try to, it's like I was trying to provide a bit of a playground for you so you can create a file and then see what happens. So I made the file. Let's see what is in the file. So this is here. This is loading up all the global meta attributes. On the test object, the test instrument, we have test keywords as part of testing, test clean, test init, all that. So that got written too because it was part of our global metadata. Pysat version, that gets written there too. Conventions, I'm letting you know, it's Pysat simplified SPDF, ISTP, IACG for netcdf. It's a mouthful. More stuff. Here you go. That's and did I not set? I might need to use meta. Yeah, I missed the keyword on that one. All right, so that's showing you the metadata. You can also list all the different variable metadata so you can see all the different stuff that we've written. So like for epoch, it defines the units, milliseconds since the time, long name, the calendar format, var type. So like this var type format, time-based, time scale, monoton, these are all things that are required from different file people, right? Within Pysat, you don't need to know the format, it's a thing. Epoch gets special stuff because it's singled out by file format standards. All your other different variables will get, like we normally carry on units, the long name, notes, description, the min and max values. Here you can see the multiple fill values that we've got. Cover every use case, no matter who's loading it, they'll get the fill value. Depend 0, this is a CDF, I mean a CETA web requirement, display type, that's a CETA web, var type, all that. So there's all your different files, I mean variables. You can also load the data back in using Pysat. So we've got a load netcdf routine. It's general, it's pretty generalized. And it's all set up. Oh, sorry.
No, I had a question.
Yes.
If you go, we can have this discussion offline if you wish, but why did you say it's a simplified version of the ISTP compliance?
Because we didn't quite do everything that they did in the icon one. The support is there, but like, okay, so let me give you some specifics. Oh, here we go. Like units, the official one is like a big U nits, and I think there might be a couple. Long name gets a description, has like for C, it might be like cat description. Yeah, so there's a lot of different case changes and things like that that are kind of small that I'm just not doing for the basic Pysat thing.
Because, well, having a standard helps for interoperability, you know, so if you share the data, then if the standard is the same, you can use it blindly in other tools.
Yeah.
I'm sure you know what's behind all this, but
yeah.
So yeah, so I was a bit surprised that you say simplified, and I was wondering what was the extension of the simplification, but we can discuss that later.
Okay, I'd be happy to. I can't say that Pysat does make files completely standards compliant with the full standard. It just takes some options, which Like all these are set up that the whole demo is set up that you can come up here. I'm just doing the 1D data right now, Pysat testing. We also have like this multi-dimensional data that's in Pandas and this testing 2D. We've got a simulated test model, so that's got higher dimensional data. Similar with this other one. And then you can come down here and you can play with some of these options. So I can change, let me uncomment this. So this is going to be a meta translation. So what I'm telling here for this meta translation, I'm going to tell Pysat, hey, I want you to take this label. And when you write the file, instead of using that name, I want you to use these names. And similarly for the fill val, let's do funny fill serious or whatever. And then you can define an inverse translation as well. So when you load the file, Pysat knows, oh, I've got redundant information between these two. After I make sure the information is the same, I'll rename it to something else. So if I define this here, I write the file. That looks like it wrote. That's the global. Here, let's do the, here we go. Funny units, serious units, funny fill serious. So it's pretty trivial that if you want to go, oh, I'm going to follow these standard, you put in the things that you want at the end. And when Pysat's actually fully released, or you go check out the RC, in the section on writing files, I actually do a specific example for the full ISTP, whatever standard. I just thought it might be a little too much for the demo, but yeah, that's fully up there. So this one, I'm running out of time and there's a lot of options, but this one is meant like a playground. You can go through, you can pick any of the instrument objects, write the file, look at the file. You can change any of the meta translation, the inverse translation. It looks for nans. There's other things. You can, I've put in some, example ones to start with. You can just uncomment those lines in here and everything should still work going down. And then you can also load it back up into Pysat and undo all that extra file standard stuff. So then when it goes into Pysat, it's exactly like people would expect. This should work. Oh, look at that. So I passed in that meta translation and other things that were defined above. And so it's going to, should have done the metadata, not, oh, here we go. So you can see the funny units and serious units is gone now. I just loaded that same file where if you look at it raw, like this, or I mean, raw like this, right? It's all written in there, but in this case, I'm undoing all that as it gets loaded back into Pysat. So there's really a lot of versatility here. It can take a lot of time on doing files. So I'm trying to help out the community and make it simpler for them and perhaps more consistent. So the simplified standard is more for like, hey, I'm going to send it to a colleague or something. Who cares if it's capital units or anything like that? It's enough that people should be able to understand. But if you want to support something that's fancier and all that, then that is totally doable too in the same way. So you don't have to do it. You just account for it when it gets written. And there's more parameters and stuff that can be added, but I don't have time to show that. So there's only like 4 minutes left. Well, let me look at Slack. No more Slack questions. Hopefully that's okay. Summer school, Pysat. So that's the files. And this one here, I'm doing just a demo with Pysat missions. So this is simulated orbit propagation and all kinds of other stuff. So it's not technically like a loaded file, but you use Pysat in the exact same way as you would anything else. And you can, I've got orbit iteration and other things in there. This is a big one that I'm not going to be able to show, which is it's a bit of a bummer, but this is a demo of Pysat season. So this is that generalized bin averaging thing that I was talking about before. So this is, this type of code is something that you can just like turn a crank and almost pop out science papers. So here, this is a bin average of IVM drifts and density over local time and longitude. And this demo here, in principle should, will work for any instrument supported by Pysat, not just 1D data, but you can do the model data and all those other things. So you can, there's generalized analysis that's completely possible and supported by Pysat. Not just bin averaging, you can do occurrence probability. So I have like occurrence probability. One of the things I'd use this for is how often do equatorial plasma bubbles form? That's generally a hot topic for space weather. I think the best way to do that is to look at the occurrence probability by orbit. So that's in there, but you also can do occurrence probability by day. So this is just a high level function. You define the data that you want, and then you go, hey, Pysat, give me my occurrence probability by orbit. And this is a 2D distribution of bins. It'll go through the full season of data that you supply and completely do the average. So for something like this, if we didn't have that custom function things, the only data you could operate on is the stuff that comes directly out of the file. But with this, you can add whatever parameter you want. You can modify parameters, whatever you want. And you don't have to modify the occurrence probability code or the seasonal binning code or whatever. You just alter your instrument object. And then here's all the different options with loading. You can load by date, year, day of year, day of year, by date times, by file names. You can do one day, you can do a range. You can load all the data on demonstrating the custom modules. And then down here is the data padding for time-based calculation. So this is really important if, like if you're doing the plasma bubble things, you might be doing something based on wavelets of Fourier transform or anything like that. You need some time range. And this makes your data set effectively continuous, so you don't ever have like that stop-start problem. Here I show all the different iterations. You can have different days and steps and all kinds of different stuff to go through the data. This one is all the instantiation options and general parameters that you could want or maybe don't want. But there's a lot of different things, a lot of different information in Pysat, which I knew I wasn't gonna have time to talk about, so I just wanted to put it in something. I know it's the last seconds. And then data access and assignment is the last demo. I ran out of time and I forgot to do metadata, but I think it's pretty straightforward. So I am out of time. Thank you so much for your attention and questions so far. If there are any final questions, I might have time. If Julie, maybe.
If anyone has a question or two they want to ask, we can go ahead and ask it. Otherwise, thanks, Russell.
Thank you.
If you have any questions for Russell, be sure to find him during the break. We'll
Yep.
go ahead and break now until 6:15 local time.
Thank you.
There we go. Hey, Eric, you online?
Yes, I am.
Cool. I sent you some DMs on the Zoom chat just now. Hey, Eric, if you want to bring up your slides and stuff, you can do that now.
All right. Okay, can you see my screen?
Yeah.
Cool.
Okay, everyone, we're gonna go ahead and get started again, so sit down. Next up, we have PySPEDAS with Eric Grimes presenting remotely. So whenever you're ready, Eric, go ahead.
Right, so can you read my screen? Can you see everything okay?
Can see it, but if you can zoom in like 2 more, maybe, that'd be good.
Like that?
Yeah, that's great.
Oh, cool. Right, so I guess I can go ahead and get started. So I tried to open up the Slack space on another screen, but it's not letting me, it's telling me to sign in for some reason. So I can't actually see that on my screen.
We'll say the questions out loud to you.
Okay, cool, thanks. So for those of you who don't know me, I'm Eric. I work at UCLA in Earth, Planetary, and Space Sciences. I have my email here at the top of the notebook. It's just egrimes@igpp.ucla.edu. And most of the time we handle support emails or support requests and feature requests and such through email. So feel free to email me anytime. I get a lot of emails, but that just means I've probably already seen whatever questions you're coming across. So feel free to email me anytime. And if I haven't already seen the questions you have, it'll be good to add them to the list of questions I've seen. So for this notebook, I tried to start at the sun and go all the way down to the ground. So we start with solar emissions first. So we start with solar emissions first and then go all the way to the ground and look at data throughout the heliosphere, essentially. And for the most part, I tried to use data from March 27th, 2017. So for everything other than 2 missions, we have data for this date. The 2 missions that we don't have data are Parker Solar Probe and Solar Orbiter. And those hadn't launched yet, so we're using more recent examples for those. And another important thing to note is that only a few data products are loaded and plotted for each spacecraft in this notebook. So not all spacecraft instruments and data products are demonstrated. It's just a handful of the hundreds available. And so for a full list of the capabilities, go to our documentation. It's just pySPEDAS.readthedocs.io. And I actually over here. So once you go to the main page, we have some simple copy paste examples on the home page that shows how to plot the magnetic field data from 4 spacecraft. But for the full load routines, just click load routines on the left-hand side, and it lists should list all of the missions that we have data for. And then, for instance, you can click on one of the missions, like say Geotail. And so we have the documentation from the for each instrument on Geotail, along with the doc string. So you have the full documentation. And then we also have copy paste examples for each instrument. So you should just be able to copy and paste these examples. And once you have PySPEDAS installed in your environment, and you can just create figures.
Do you have a camera you can turn on, Eric?
No,
Okay.
and
no
my
worries.
laptop's closed. Anyway, I'd prefer if everyone just focused on the presentation rather than me.
Fair. Could you also zoom in 1 more? Sorry, we need 1 more.
Yeah, let's see. 200.
Cool.
Let's try to. I guess this left-hand side doesn't. There we go. And so all of this depends on other projects in the PyHC community. So all of this depends on CDF-lib. So we use CDF-lib to actually load the CDF files into memory. And PyTplot, PySPEDAS is essentially just a wrapper around PyTplot. So a lot of the examples I'm going to show today are really PyTplot examples. And we have a wrapper around Geopack that allows you to generate field models using SIG-and-Yinko field models at positions. We also, in this notebook, we're going to show how to use data loaded with PySPEDAS to do some calculations using PlasmaPy. And we also load some data with the Happy client towards the end of the presentation. So in the HelioCloud environment, PySPEDAS is already installed, but I put the install here at the top in case you want to upload this to Google Colab or a different environment where PySPEDAS isn't installed. So to get started and install the latest version, just do pip install PySPEDAS, and it should go out and install it. And if you want to install the latest bleeding edge, so I also included some examples here of installing the latest bleeding edge. So we're doing development on GitHub. So to grab the latest bleeding edge of PySPEDAS, it's just the PySPEDAS bleeding edge or repo. And then you say the folder is archive. So the archive folder, and then you give it the branch name. So the main branch is called master. So it's just master.zip. And you can do the same thing with the pytplot package to install the latest version of that. It's just the repo and then archive folder and then matplotlib -backend, because we're doing all of the development under the matplotlib backend branch right now. And so to get started, you just import PySPEDAS once it's installed. So it's pretty straightforward. But before you actually start loading data, you should note that by default, the data files are saved in a subfolder of your current working directory. You could change this by setting various environment variables. The main one is speedas _data _dir. So if you set that, it should put all of the data under your whatever folder you specify in that environment variable. The directories for individual missions can also be changed by setting the mission specific environment variable. So for instance, PSP _data _dir sets the Parker Solar Probe environment variable or data location, and solo data dir sets the solar orbiter data directory. And these would override the SPEEDAS data dir. So you can have one SPEEDAS data dir for most missions and then have mission specific data go into a different folder. And so in this example, I tried to set it to the shared folder initially, but since that's read only now, can't download data to that folder. So it's commented out at the moment, and it actually wasn't working last time I tried anyways. It worked about a month ago, but something happened with the HelioCloud platform and it stopped honoring our environment variables set inside the notebook. But outside of the HelioCloud environment, you can set the environment variables inside the notebook and it should work. And so one more thing to note is the load routines in PySPEDAS all follow the form PySPEDAS.mission.instrument and their functions. So you just call that function and it should just load some data. And all of them have the same core keywords, or at least a central set of keywords for accessing the data, like T-range, specifying the time range, level, data type, etc. And some missions can have more keywords to add more flexibility for how you can load the data. And I'll show some of those, some load routines that have additional keywords in a little while. So to find the supported load routines and the keywords, of course, go to our documentation. They should all be listed there. Again, on the left-hand side of under load routines. And you can also call help on the load routine you're interested in Python. So for instance, you just call help on pyspedas.solo.mag. It'll print out the information to help the doc string on the mag function. And one more thing to note is that the function names, we tried to follow the instrument team's names. So Solar Orbiter calls their magnetic field data mag. So it's an instrument name is just solo.mag. Other missions have other names. For instance, I think the Japanese missions tend to always use MGF for the magnetic field data. So we use, for instance, Geotail, we use MGF, and Arase is MGF. So we use the nomenclature from the name or from the mission team and the instrument team. We try to adopt their names. So it should match whatever's in the release notes or the data products guides for the data products you're looking for. And so calling help on the instrument load routine here, you can see it prints out the defaults for each keyword, as well as a list of the keywords and what they do. So you can see we try to make it where if you call the load routine, so it's, for instance, if you just call pySPEDAS.solo.mag, it will load data for some default date. In this case, it's June 1st, 2020, and it loads magnetic field data. It loads magnetic field data and RTN normal coordinates and level 2. And you can see that, but if you want to change the default, you can set them by specifying, for instance, the T range keyword to specify a time range, data type keyword to specify a different data type. I mentioned that by default, it loads RTN coordinates in normal mode. But if you specify data type equals RTN normal 1 minute, it'll give you the 1 minute data. RTN burst allows you to load the data, the RTN coordinate data in burst mode. And there's a level for changing the level. And suffix for appending a suffix onto all the loaded variables. And by default, it only loads the science data which, from the CDF files. So some variables in the CDF files are labeled as support data. To get those variables, you'll have to set get support data equals true. So we don't, and this is specified by the var type in the CDF. So usually we load all the data with the var type of data, but not, and we ignore the support underscore data. But if you need to get access to those, just set get support data equal to true. And a really useful keyword is var format. This allows you to limit the variables that are loaded. So it accepts wildcard characters. I think it also accepts regular expressions, but I'm not entirely sure. By default, it just the load routine will load all of the support or all of the data, all of the variables that have a var type attribute of data. But you can limit that with var format. You can also, if you know the exact names, you can also limit the variable names that are loaded with the var names keyword and just give it a list of variable names to load. So this helps if there's a whole lot of variables, but you're only in the file, but you're only interested in one, and you happen to know the name of that variable. You can ignore loading all the stuff you don't want and only load the data you do want. And so we also have keywords for downloading the data, but not loading the data into CD or not loading the data into tplot variables. So if you set download only equal to true, it'll just go out and grab the CDF files and it won't actually load them into memory. And we have a keyword no tplot, and this will return the data in hash tables instead of creating tplot variables. So it has the data just stored in NumPy arrays and hash tables. And essentially the key is the key at the top level, or the keys at the top level are going to be the variable names, and then those variable names then match to or map to hash tables that didn't have the data stored. I think so those map to hash tables that have the data stored, and they also have the time stored. So this is useful if you have trouble loading a variable into tplot variable and you just want to try to load it in the NumPy arrays instead. And we have a keyword no update. So if you set this, it only loads the data if it exists locally in your local cache or in your local machine, and it won't go out to the web and download the latest versions. And then finally, time clip. This tells the load routine to time clip the variables exactly to the time range specified in the T range keyword. So the thing to note about this is that for most missions, we don't time clip by default. So if you say if you only request 10 minutes of data and the CDF file has a whole day's worth of data, if you don't time clip, it could load the whole day's worth of data instead of the 10 minutes that you request. The reason we do this is because it could, since a lot of CDF files have a bunch of extra variables that you're not interested in, it could take a while to actually do the time clipping operation by default. So we give the users the option to do the time clip. If you don't do that and you want to zoom in, I'm going to show later how you can quickly zoom into variables. So a faster workflow rather than loading the data and time clipping all the data is often to just load the data and then zoom into the time intervals that you're interested in. So I'll show an example of that in a little while. So now that we have a general overview of the solar orbiter magnetic field routine, we can load some magnetic field data for solar orbiter and RTN coordinates, and by just calling pySPEDAS.solar.mag. And in this case, we're changing the time range from the default, and we're just doing 2 hours of data on April 20th, 2020. And this time we are actually telling it to time clip the data. So we should actually get 2 hours of data. And you can see it went out and looked for the file. It found that the file that I already had loaded or downloaded was current. So instead of downloading it, just loads the data from local cache. And you can see it time clipped the one variable that it loaded, which is BRTN. So it's the B field in RTN coordinates. And now we can use pytplot to create a figure, to actually create a figure showing this B field. So to get started with that, you just import tplot. This is a tplot function from the pytplot package, and then call tplot on your variable. So just call tplot and then give it BRTN. You can see it created a figure of the magnetic field in RTN coordinates.
Hey, Eric,
And yes.
quick question from the chat. Is the slash between the date and time specific to solar orbiter's time variable?
No, so the T range option is very flexible. You could do like this and it should work. You could do like, let's see. It uses fuzzy parsing. So you can do something like this. Just load the full day. So it's very, very flexible. So you could also do down to, so that's down to minutes. You could do down to seconds. You could, so in this case, we did the full day, but you could do just. So I think that answers it, but this is should be extremely flexible because it's doing fuzzy parsing. And so if it can figure it out, it should be able to.
Great, thanks.
All right, so back to the plot, you can see we now have 2 hours of data, exactly 2 hours of data. And one thing I could note is that, see that the CDF file here is a full day's worth of data. So had we not time clipped the data, it would have it would have plotted the data for the full day, even though we requested only 2 hours of data. And this is, so it only gave us 2 hours of data because we explicitly set a time clip keyword. And notice that the y-axis title has the title, it has the units, it has the legend, including the colors of the colors of the lines and what they mean. So this is really the beauty of pytplot, is that we can take all of that information from the CDF file about the data, and we can store it in these pytplot variables. And then we could easily create plots and figures with these variables because we have the plot metadata stored with the data, along with things like units and the coordinate systems. So it's a very powerful model, I think, as we're about to see. So for some Parker Solar Probe data, I took this example from one of the PSP team's IDL crib sheets. So essentially just tried to recreate the same figure as in their crib sheet. So we take a time span for 4 days near perihelion 2 and load the magnetic field data and the radio frequency spec data. So set a time range, and in this case, it's 12 hours of data. And so we're also specifying a certain data type. I think by default, it loads the mag RTN data. But in this case, we're loading the exact same data type that they were loading in the IDL example. And for the radio frequency spec data, doing the high frequency and the low frequency, And I also explicitly set the var names keyword to tell it to load only one variable, and that's this variable. And in all of these cases, we are loading or setting time clip to exactly those 12 hours. And so you can see it went out, it looked for the files, it found that we already had it locally, so it used it. File is current, and same deal with the RFS HFR, and same thing with the RFS LFR. And it only loaded, note that it only loaded the variables specified in var names for the RFS data. So by default, we might not get all of the plot metadata that you want on a variable. So sometimes you'll have to set it manually. So in this case, we're going to set some, we're going to use options from pytplot, the options function, to set some options on some spectra. So to do that, you just import options from pytplot and then call options. And the first argument is the variable name, second argument is the option name, and then the option value. So for this first line here, we're setting the y-axis to a log scale, setting the z-axis to a log scale, and doing the same thing for the low frequency data as well. And then we're also setting the legend names, so that's the labels and the legend on the magnetic field data and RTN coordinates. So BR, BT, and BN. So you can see now we have, so we're gonna, then we call tplot function just as before. This time we're giving it a full list of variables. So at the top, it should be the magnetic field and RTN coordinates from PSP, and then the radio frequency data, and the high frequency data, and then the low frequency RFS data. And this figure looks pretty much exact as the figure that was created by the IDL team, or the fields team's IDL example. I think they also have a data availability bar or data quality bar, but we don't have that in PySPEDAS yet, so I wasn't able to add it here. So that's the Parker solar probe and the solar orbiter data. And I mentioned that we used other dates from those missions because we didn't have any data for our 2017 case or 2017 case. So now we're gonna switch back to our May 27th, 2017 case by just setting the time range to that date, the full date. And then we can load some ACE data, some magnetic field data measured by ACE. So it's PySPEDAS. So the magnetic field data from ACE is pyspedus.ace, so that's the mission, and then MFI for the instrument. And again, we try to use the instrument team's name for their function names. So MFI matches the ACE team's name for their MFI instrument, just the magnetic field instrument. And so the only keyword we're setting here is T range for the time range. So we should be loading data from May 27th here. And you can see it created variables. It loaded magnitude, BRTN, BGSE, and BGSM. So we can plot the data in the B field data in GSM coordinates, just calling tplot and giving it that BGSM variable name. And note in this case, it didn't add the labels and legend names by default. So we don't have that. You can plot the magnitude and the vector in GSM coordinates. In this case, it actually did put a label on the magnitude, but not on the vector for some reason.
Quick question, Eric.
Yeah.
Do you know if pytplot has more colorblind friendly color schemes?
It's a good question. You could change the colors to whatever, because it's matplotlib the backend is matplotlib. So you can change the color bar or colors to whatever matplotlib accepts. By default, we're trying to use the same ones as IDL SPEDAS, so everything looks the same. But you can, and I will show an example later of changing color bars for spectrograms. But all these, I'll also show an example of changing the colors. But we accept any colors that Matplotlib accepts.
Cool, thanks.
So now we see the ACE MFI magnitude on top and the ACE B field in GSM coordinates down below. And so we can, I mentioned that by default here, we don't have the legend names set. We could set those legend names just by using the options function, just giving it the variable. So it's BGSM, the legend names option, and then give it what each line stands for. So first it's BX in GSM coordinates, then BY, then BZ. And then we can recreate the same figure as we did before. And now it should have the legend names for each line. So BX, BY, and BZ. And that's all just set by options and using legend names. I think nowadays labels also works, but I tend to just use legend names. So another instrument, we can load data from the SWE instrument. So it's the solar wind electron proton and alpha monitor. And so that's just pySPEDAS.ace.swe. You set the T range and went out and looked for the file, found that the one that we have already saved locally is current. So it says file is current and just loads the local file. And you can see it loaded some density data, velocity data, temperature data. So this is probably flow velocity, or this is probably the speed, and these are the vectors. So we can create a plot with a bunch of t-plot variables. So you just call t-plot and give it the magnitude. So that's going to be the magnitude of the B field on top, and then the B field in GSM coordinates down below. Then we can plot the velocity in GSM coordinates. So that's the VGSM here, and then VP, that's going to be the speed, the hydrogen speed, and then the density, NP. See, we have the density down below again. And again, notice that it picked up it got the units from the CDF metadata, so it includes those automatically. So we have kilometers per second on the speed and the velocity. And B field has the nanotesla, and the Y subtitle density is number per cubic centimeter. And so what if, yeah?
Sorry to interrupt. Another extension to the color bar thing. Is it possible to pass through whole color maps to PyTplot?
So it is if you're working with spectrograms. And I'll show an example of that later.
Thank you.
Yep. So what if you want to increase the size or decrease the size of a figure? As you add more panels and more data types, you probably want to change the size of a figure. So we have keywords for that in the tplot function. So X size and Y size. So when you create the tplot, when you call the tplot function, you just give it your list of tplot variables, and then you could say increase the X size, and this is measured in inches. So instead of and of course you can call help on tplot to find the defaults for these. But in this case, we're doing 15 inches and making the Y size 20 inches. So we're drastically increasing the size of the figure. You can see it, essentially the only thing that changed is the size of the figure. So plotting the exact same figure, except now much larger. And I'm going to show how to change the font sizes and all of that soon enough as well. So we can move on to a little bit closer to Earth and look at Discover data. So we can load and plot some Discover magnetic field data, since we've been plotting a bunch of magnetic field data. And that's just, again, calling PySPEDAS.discover.mag and set the T range keyword. And again, we already had the data stored locally. So it found the local data file and just loaded those data. And then we plot the data. It created these variables. So we created the variables in GSC coordinates and in RTN coordinates. So we can plot the data and GSC coordinates on top and RTN coordinates on the bottom. And again, the legend names are missing, so you could add them just by calling options. So in this case, instead of setting it to something reasonable, I'm gonna show how to change the colors and then change the legend names to match those colors. So on the GSC variable, we call options, give it the GSC variable name and give it the color option, and then give it the colors for the different option or for the different lines. So we're going to change the X component to purple, the Y component to green, and the Z component to black. And then we could also update the legend names with the actual colors that they match, and then call tplot on that variable. And notice that the colors of the lines were updated and the legend names now match those colors. So if you ever load some vector data and it doesn't have the legend and you want to add it, just import options and then call options on the tplot variable and set legend names or labels. Labels should also work. So moving along to stereo, you can load some magnetic field data from stereo. It's just pySPEDAS.stereo.mag and give it the T range. And I should also note that I mentioned earlier that we're only loading a few data types. Like for instance, for Discover, while we loaded magnetic field data, we also have Faraday cup data, we have orbit data, and attitude data. And then there's another function that loads called .all that just loads all the data at once. And so you can call PySPEDAS.discover.all, give it your time range, and it'll go out and try to load the magnetic field data, the Faraday cup data, as well as the orbit and attitude data. So that's just one example of how we're just showing just one instrument and one data type for one instrument, whereas we have support for a lot more here. I encourage you to go through our documentation and try these simple copy-paste examples. So back to stereo. So to load magnetic field data from stereo, it's just pySPEDAS.stereo.mag. And you set the T range keyword to give it the time range. And again, I'd already preloaded these files, saved these files. So it's going to say, so it says file is current. If the file isn't in your environment, it goes out and downloads it. And you can see it created a new variable called B field. So in this case, we don't know what the coordinate system is. It just loaded a variable called B field that doesn't actually have RTN or GSC or anything in the name. So we can't figure it out. But since we can't figure it out from the name, we can easily look at the metadata from the file. So to do that, you use the get_data function from pytplot. So for instance, so STE here stands for stereo, and we're going to stereo metadata and call get data on our B field variable. That's that variable that we loaded up here. And the one thing is that we have to set the metadata option to true, and that'll tell it to return the metadata rather than the actual data. So get data without metadata option returns the actual data and the time values. And I'll show an example of that a little bit later. But for just the metadata, you just set metadata equal true, and it'll return a hash table that has the various metadata. So, if we want to find the coordinate system for a variable, so we just look at the variable attributes from the CDF and the metadata. So this has the metadata, and then we give it CDF, and then VAT, and it should have the variable attributes. So you can see magnetic field vector and RTN coordinates from the impact mag instrument. So you can see it's in RTN coordinates, even though it's not in the name, but we can figure it out just by using the metadata from the CDF file. And another thing to note is that in this case, it loaded the magnetic field data from Berkeley, because that's where the data files are. Different instruments and different missions will load the data from different repositories. A lot of missions and instruments support loading the data from CEDAWeb or the SPDF, but a lot of instruments also support loading data from the official repositories. For instance, MMS loads the data from the Science Data Center, but there's an option for turning that and loading the data from SPDF. Themis, I think, loads the data from Berkeley. The Arase data is almost certainly loaded from Japan. So you can figure out which data or where the repository is by looking at just the output from the loader team. So in that case, we noticed that it was loading the data from Berkeley. For the magnetic field data from Stereo, for the plastic data from Stereo, it loads the data from NASA. And we just call pySPEDAS.stereo.plastic to load those data. And you can see, since it shows the remote data index, you can see where it's actually grabbing the data files from. And in this case, we had already preloaded it. So it said the file is current, so it's the same file. And then it loaded a bunch of the data from the plastic instrument. And so now we can plot the data from Stereo. So we have the B field on top, that's in RTN coordinates. We have the proton number density, the proton bulk speed, and the proton thermal speed. And again, notice that it actually got the units right. We didn't have to add units to anything. It just it extracted them from the CDF metadata and is using them in the plot. So now that we've already loaded data from a bunch of different missions, what if you want to actually find the tplot variables that are currently loaded? You're probably going to forget the names or have to remind yourself of the names. So tplot has a function called tplot_names. So you just import that from pytplot and then call that function, and it'll list all the currently loaded tplot variable names. And notice that they're in the order that they were loaded. So the data that was loaded first is going to be first in the list, and the data that were loaded last, like the Stereo plastic data, are going to be the last variables in the list. And this is also a function that returns the list. So you could say vars equals, and it'll create a variable named vars and with the list of the tplot variable names.
Another question.
Yeah.
So a question about Stereo, because it wasn't mentioned or I missed it. I assume it only uses Stereo ahead since Stereo behind is not active anymore.
So I'm not sure when the stereos were when the stereo, in this case, we're loading ahead for 2017, but you should be able to switch to behind by, well, the easiest way is to look at the documentation. Go to Stereo, and I think it's probe. So probe A, yeah, I think probe A is ahead and probe B is behind. And by default, all the load routines are loading ahead. So if you change probe to B, it should load the behind data, assuming that that data actually exists for this time range.
Gotcha.
But by default, it loads ahead.
Okay, cool. One other question while I have you. Does this support variable name prefixes to help differentiate between data from different missions?
So it does. I think all of the load routines support suffixes, but internally, so you could say STE plastic, and that'll append a suffix to each one. For prefixes, you would have to update the actual load routine because the underlying tools from pytplot support the appending prefixes, but the actual load routines don't, if that makes sense, unless it's exposed by that team.
Cool, thanks.
All right, so next up, we're going to use get data. Instead of extracting the metadata, we're going to actually use get data to extract the times and the data values. So to do that, we already had it imported from before, so you just call get data on a tplot variable that you're interested in. In this case, we're going to be getting the data for some proton number density data. And if we just print out data, you can see it returns a named tuple. So in this case, it's a 2-element named tuple. And the first element are the times, and the second element are the Y values. And the times are Unix times in UTC, and the Y values are just actually the proton number density values. And so the opposite of get data is to store data, store underscore data from pytplot. So I mentioned that time values are stored in X. So the data values are stored in Y, and spectrum variables, data.y contains the actual data values, so like the z-axis values, and data.b contains the y-axis values at each point. And I'll show examples of all of this very soon. So to create a new variable, you just import store underscore data from pytplot, and then call store data, and give it your new variable name. In this case, we're going to call it ste proton n. And then you give it the data keyword. And that accepts a hash table. It should have the X values specified as, or the time value specified in X, and the Y value specified in Y. And it returns true if it created a variable. So one thing that I do regularly is do saved equals stored data, and then you could do like if saved and do something else. So you don't accidentally try to do something on a variable that wasn't actually created successfully for some reason. So now we can call tplot on our new variable that we just created. So it's proton number density, and then the original variable. So we have the loaded from the CDF file. So we have our variable on top and their variable on the bottom.
How do you get the data units and then add them to the plot?
So data units. So I think I'm going to have an example of that later,
Okay,
of adding them to the plot.
I'll let them know.
But yeah, the units, you're almost certainly going to want to use, if it's not extracted automatically, you're going to want to use the get data trick that I used earlier, metadata. So in this case, it has the units and the CDF variable attributes here. It's just units. So all you have to do is call get data to return the metadata, and then look at the variable attributes from the CDF. And I'll show how to actually add that to the plot soon enough. All right, so one thing to note here is that our variable doesn't actually have the metadata. So we just gave it the times and the data values. It doesn't actually have the units already specified here, and the name density, since it extracted, in this case, it extracted that from the CDF metadata. But we didn't actually provide any metadata for when we created this one. So it doesn't have it set. But I will show how to change that in a few. All right, so next up, we can load some Omni data. So this is getting closer to the magnetosphere. Omni data is essentially the solar wind data that's been time shifted to the magnetopoles. So to load the Omni data for the full month, this time we're going to load the data for the full month of 2017. That way we can get context around our event, which is only a single day. So you just call PySPEDAS.omni.data, give it your time range. And so the Omni routine is one of those, might be the only routine in PySPEDAS that time clips by default. And that's because the Omni data files are stored in monthly files. So you can see it actually goes out and downloads the full month anyways. So usually people are requesting less than a month of data, so we automatically time clip the Omni data by default. But in this case, since we're requesting a full month's worth of data, there's no need to time clip. So we told it, don't time clip the data. And so it went out, it tried to download the latest file, it checked out the latest file, found that we already have it stored locally in the cache. And so it just loaded that. And you can see it created a bunch of variables. So we have the one thing to note about the Omni data is that instead of storing the vectors as single variables, it stores the components. So they have bx, by, and bz, vx, vy, and vz. So and some projects do this. So we have some utilities in pytplot to work with these components. For instance, you can join vector components into a single variable using joinvec from pytplot. So to do that, you just import joinvec from pytplot and then call joinvec on. So you give it the list of vector components first. So you give it your bx, by, bz, and then give it the new name. So new tvar is the keyword to set for the name, and just tell it you want it to create a new variable called b_GSE that has these three components, bx, by, and bc. And the one thing to note is that all of these have to have the same, have to be on the same timestamps. If they're not, it's going to complain. It's going to error. But they are in this case, since they're all essentially the same vector. They're just different components and stored in different variables. So when you call joinvec, it should create a new variable called b_GSE. And again, in this case, they have vx, vy, and vc, but they don't actually have the coordinate systems in the name here. So we can find out what coordinate system by check what the coordinate system is, again, by just checking the metadata. So say metadata equals get data and give it the variable name. So in this case, we're looking at the velocity, the x component of velocity, and set metadata equal true. And then you can look at the CDF variable attributes, and you can see it's Vx velocity, it's a GSE coordinates. And again, it has the units in here. And I think that's part of the ISTP standards. So any of the load routines that load data from ISTP compliant CDFs should have the units and the coordinate systems and everything in the CDF metadata, the variable attributes. And so we can, since we now know that these are that the velocities and GSE coordinates, we can use joinvec to join the velocity variables components into a single variable, just like we did with the B field. We'll call it v_GSE. And then we can update the legend names so that we actually have legends. So we can call options, give it the variable, so bGSE and vGSE, give it legend names, and then say it's bx, by, bz, as well as bx, by, and bz. And then we can create a plot of the omni data. And we have the magnetic field data at the top, and the velocity data, the velocity vector below that, and then the flow speed, and the proton density, and SimH. And again, notice that it doesn't have the units. Probably should have joined the units from joinvec, but it doesn't at the moment. So you'll have to set the units here for bGSE and vGSE. And you do that by calling the options function, giving it the variable name you're interested in, and then the Y subtitle. Of course, Y title is the top one, and then is the top level, and then Y subtitle is the next one below it. So we pretty much always put our units in the Y subtitle option. So in this case, we're updating the bGSE vector to have units of NT, and then the vGSE vector to have kilometers per second. And another useful option is to change the Y scale to logarithm. By default, that's going to be false unless it's in the plot metadata or in the CDF metadata for it to be a log scale. But we can change it to true and tell it to plot it always on a log scale. And then we can recreate the exact same plot as before. And you can see it now it has the same plot, except now it has the units and the for the B field and the velocity, and the proton density is on a log scale now. Notice that that's actually switched to a log scale. And so it's worth pointing out also that the opposite of joinvec is splitVec. So if you have a vector stored as a single variable, you can split it into individual components just by importing splitVec from pytplot, and then call splitVec and on the vector that you're interested in, and it creates creates it turns the components into their own variables. So we have an X component, a Y component, and a Z component. And now we can plot the individual components. And again, it probably should have added the units here now that we've added the units, but it's not carrying that through. We're gonna have to fix that. But it did actually split the vector into 3 variables with their components. And so one useful routine is coordinate transformations. So we have PySPEDAS.cotrans for doing coordinate transformations. So this supports most of the geophysical coordinate transformations. So to try that out, you just import cotrans from PySPEDAS, and then you call cotrans and you give it the name in for the variable you want to transform, the name out for the output variable name. And in this example, the input coordinates are in GSE coordinates, and the output coordinates we want to be in GSM. So we just call that function, and it should have converted VGSE and created a new variable called VGSM with the data in GSM coordinates. So now we can call tplot on VGSE and VGSM. You can see now it has the velocity data in GSE coordinates on top and the velocity data in GSM coordinates on bottom. And notice that internally in the cotrans routine, it actually updated the coordinate system in the legend and everything. All you have to do is do this one call to do the coordinate transformation, and it updates the plot metadata as well as actually doing the transformation. So another really useful geomagnetic index is the Kyoto DST data. And so this is essentially basically a storm time disturbance index. And so we have a load routine that loads that data from Kyoto. So it's just pySPEDAS.kyoto.dst. You give it your time range. In this case, we're loading the data for the full month of March. Again, since we loaded the Omni data for the full month of March, might as well load the DST data for the month of March. And you can see it created a variable, Kyoto_DST. And of course, we can then plot the DST data and the SIMH data. So the SIMH came from the Omni data. So we have Kyoto on top and SIMH on the bottom. So the thing to note is that DST data is hourly, and the SIMH data is I think it's minutes by minute. It's either minute data or 5-minute data. I'm not sure. I think both are available. We can easily check. By default, it probably loads the 5-minute data. And nope, loaded the 1-minute data. So that's 1 minute SIMH data along with 1 hour DST data. I think SIMH data also has more stations, but they're very similar for small storms. So what if you want to combine 2 variables, 2 tplot variables? One way is to use get data to extract the variables, the data, and then use store data to create an entirely new variable, interpolate everything to the same timestamps. Another way is to just create what's called a pseudo variable. So to do that, you call store data, give it the name of the pseudo variable, and then instead of giving it a hash table, instead of giving data a hash table, you give it a list of tplot variables to combine. So in this case, we're telling it to create a pseudo variable containing DST data and SIMH data. And now we can plot the DST data and the SIMH data in the same panel just by plotting this new pseudo variable we just created. And by default, right now, it uses the metadata from the first in the list. But you can override that by calling options on your pseudo variable. So for instance, you can call options on our combined variable, set the Y title to say DST and SIMH. You can add the units to the Y subtitle, set the color, so blue for DST and red for SIMH. And then we could also set the legend names. So we have a legend that has which each line is, and then we can just call tplot on the on the pseudo variable. And you can see now it has, so we have the Y title was updated, the Y subtitle was updated, the colors, blue is DST, SimH is red, and they're all on the same panel. And we didn't have to worry about interpolating the SimH data and the DST data or using get data or store data. We just you called store data to create a pseudo variable and then set the options on the pseudo variable and plotted it. And so getting a little closer to the Earth, we can lose some magnetic field data from geotail. And again, it's pySPEDAS.geotail.mgf. So that's again, that's just following the naming convention for their instrument from the geotail team. And there's also the name of the data types and the CDF files. So it's consistent. The naming scheme of the load routines is consistent with the variable or with the actual CDF namings from the team. So again, we just give it the T range to load it for our time range. And we can load some data from the CPI instruments. Again, it's just pySPEDAS.geotail.cpi, give it the T range. And then we can easily just create the plot of the B field, the solar wind proton density, and the solar wind velocity. And again, notice that it got the units and it extracted those units from the CDF metadata. And so now, what if we want to take the solar wind velocity data and return the data in NumPy arrays? Sometimes you just want to work with the data values. So I showed how to do that a little bit earlier, so we can go a little bit deeper here. So to actually access the NumPy values, you just again call get_data on the variable you're interested in. And the time values, again, the Unix times stored in UTC, and they're just .times. So it's SW_v.times, and that gives you the time values. And it's just a simple 1D array of all the times for each data point. The data values are in .y, so SW_v has the data values at each time. And you can see there are nans at the beginning, but eventually we get some actual vector data. And so once you have these data, you can just use standard NumPy methods to work on these data. So for instance, you could find the shape of the data by just calling SW_v.y.shape. You can see there's 3 components and 1069 times. You want to access a vector at a single time. To find that time, you just says, for instance, you want to look at the 100th index. You could say SWV .times and brackets 100, and it gives you the 100th time or the time for the 100th element. And if you want the vector at that point, it's just SW_v.y, and you give it 100, and then you want all 3 components. So that's going to be X, Y, and Z. And what about if you want to actually work with these Unix times? You really don't want to have to implement your own routines for working with Unix times. So we provide a bunch of support routines for working with them. For instance, we have a routine in PySPEDAS called time_string. And this will convert a Unix time to a time string. So you just import that from PySPEDAS and then call time string on your, in this case, we're converting the very first time to a time string. See, it worked. And this also works on arrays. So instead of just giving it 1 time, we can give it 5 times. And it converted the each time to time string. So that goes from Unix times to time string. If you want to go back from strings to time to Unix times, use time_double. So just import that from PySPEDAS and then give it the time strings, and it should return a list of the Unix times. And
Quick question.
another use, yeah, go ahead.
Sorry. Someone noted that you could send a string to a function which works with a global variable. Is there any reason for that?
Wait, can you repeat that?
Yeah, so the whole comment was, I see how powerful tplot is, but the fact of sending a string to a function which works well with a global variable is, you know, a little nerve-wracking. Is there any reason for that?
I still don't really, I don't understand the question.
I'll post it in the chat. You can look later.
Okay, yeah, I'll have to get back to that one. So we give it the strings. And another thing to note is that this should be extremely flexible. Again, just like before, you should be able to do something like March 27. I can even do that. And that should work. So you don't actually have to know any general string format for here. You should just be able to give it whatever makes sense, and it should work. Although you should probably test that out the first time. And then finally, sometimes you might want to work with datetime objects. We have a routine for working with datetime objects as well. And that's just time_datetime. And the one thing to note is that you have to really be careful about setting your time zone, since datetime objects are time zone aware. You have to set it to UTC. When you use time datetime, it automatically sets the time zone to UTC. But if you use other datetime objects that you create yourself, you're almost certainly going to have to set that time zone TZ info option to UTC to be able to work with these, since the times or datetime objects are time zone aware. So you're going to have to be aware of that and include the UTC time zone when you're working with these data, since they're all in UTC. And if you're working with datetime objects and everything is like 5 hours off or 6 hours off, or exactly however many hours you are from GMT, then it's probably, the problem is probably a missing time zone somewhere. But by default, if you call time datetime to convert a Unix time or a time string into a datetime object, it should automatically append or attach the correct time zone. And there is a keyword for time datetime to actually override that time zone to set to a different time zone. And I actually created recently a notebook for working with dates and times in PySPEDAS. Not sure why. But actually, the best way to get to it is to go to the PySPEDAS examples in our GitHub repository. So it's github.com/speedas, PySPEDAS examples. And then buried into the notebooks, there's working with dates and times with PySPEDAS. And so I showed in this case, I showed how flexible the input strings are. So instead of giving it these like 2015, 10/16, 13/06, you could say October 16, 2015 at 13/06. So it should be extremely flexible. Back to the presentation. So we can load some ephemeris and coordinates data from MMS. The one thing to note is that for MMS data, you'll initially be prompted for a username and password. If you don't have a username and password, you can just leave the username blank and it'll give you access to all the L2 data, the public data. If you do have a username and password and you only want access to the L2 data, you could still just leave it blank, because you only really need the username and password to access the team only data, like the quick look and the scientist in the loop data, or the L1B, the unprocessed or not fully processed data. So in this case, I called pySPEDAS.mms.mech. So mech stands for MMS or actually it stands for magnetic ephemeris and coordinates. And that's just the naming scheme that they use. And again, we're giving it the same time range as before. So March 27th. And by default, MMS is going to load probe 1 for all the instruments. You could, if you want to load a different probe, you can say probe equals, for instance, 4, and it'll load probe 4 instead. And so I mentioned that the load routines for some missions have keywords for additional features. So to find all of the load or all of the available features, you call help and pySPEDAS.mms.fpi. And so that's for the FPI instrument, and it'll list all the available keywords. And so most of these are standard keywords. The MMS specific ones are like data rate and probe for the actual probe number. But by default, it loads, I mentioned probe 1, and it loads survey mode. But if you want burst mode, you just have to change the data rate to burst mode. And the plasma instruments on MMS have a keyword center underscore measurement. So this is really important if you're loading plasma data from MMS. You have to set this keyword. The reason you have to set this keyword is because FPI and HPCA are both using, so they store the data at the beginning of their accumulation interval, but all the other instruments on MMS store the data at the middle of the accumulation interval. And so when you load the data for FPI and HPCA, you have to time shift to the middle of the accumulation interval. So you're going to want to use the center measurement keyword if you're working with MMS data, especially these plasma instruments, FPI and HPCA. And so the MMS routines also have an available option. So if you set that to true, instead of going out and downloading any data, it just lists the available data files based on your requested parameters. And there's a typo here that needs to be corrected. But we also have keywords for specifying CDF version. So this tells the load routines to only load a specific CDF version, only load a minimum version, only load the latest version, the very latest version, and then only load the latest major version. So we have a bunch of keywords for working with CDF version numbers. And I also mentioned that it requests your username and password the first time you load that, and then it saves your username and password. If you want to, if you accidentally put the wrong username and password, you could give the always prompt option to any of the load routines, and it'll, any of the MMS load routines, and it'll prompt you for your username and password again. So you can overwrite a bad password or an outdated password, or update your current password. And all the MMS load routines also have an SPDF option. By default, it's going to load the data from the MMS Science Data Center at LASP. But if you set the SPDF keyword to true, it'll load the data from NASA SPDF instead. So we can load some magnetic field data from MMS. This time we just call pySPEDAS.mms.fgm. Give it the time range and load it the magnetic field data. We can load some FEEPS data. Again, it's just pySPEDAS.mms.FEEPS. And the thing to note about the FEEPS data is that we do a lot of processing, post-processing. They actually recently just changed their data files, so there's a bunch of errors that you can ignore there. But there's a bunch of post-processing that happens for FEEPS. By default in the CDF files, they only provide the individual telescope data. So when we load FEEPS data, we do a whole bunch of post-processing, like flat field corrections for ions, sun contamination removal, bad energy channel, bad eye detection and removal. Then we calculate the omnidirectional data product, and we calculate the spin averaged omnidirectional data product. So to my knowledge right now, SPEDAS, IDL, and Python are the only places you can actually get these FEEPS omnidirectional data products. So there's a lot more happening behind the scenes when you call the FEEPS load routine here than just actually going out and grabbing a CDF file. This is actually using all of the tools from the team to actually create the full science quality data product. And so I loaded some ephemeris and coordinates data. I wanted to show another tool in PyTplot here. So if you can add additional x-axes by using the var_label keyword. So in this case, we're creating a T-plot variable or a T-plot window with the PHEEPS omnidirectional electron intensity on top, and then the B field on the bottom. And then we add another additional x-axis with the magnetic local time along the bottom. You can see it has the PHEEPS omnidirectional spectra on top, and then the magnetic field data. And then notice that we have another x-axis down here at the bottom with the MLT. And the var label keyword should accept an array as well. So you can have multiple additional x-axes. So you can turn off notice that by default, the PHEEPS omnidirectional spectra has the z-axis as the color bar axis on a log scale. You can turn that off just by setting the z log option to false, and then recreate the plot. And this time it creates the same figure, except we didn't tell it to do a var label, so it doesn't have that additional x-axis. But the z-axis here, the color bar axis, is now on a linear scale since we turned that off there. And by default, the color bar is using the PyspeDas color bar from IDL, so it should be identical to the IDL PyspeDas color bar. But you can change this using the color map option in PySPEDAS. And to do that, you just call options on the spectra variable that you want to change, set the color map option, and then give it the whichever option you want. And it should accept all of the options available in matplotlib. So you can just go to the matplotlib documentation and just look at all the available options. And what I did was just pick the top one here and then change it to that. And you can see it updated the color bar.
Question from the audience. Is the PHEEPS team going to make a product with the post-processing already being done? I know this is not really
Yes.
a PySPEDAS responsibility, just asking if you know.
Yes, I think they're working on that.
Cool. Also,
I
in
think
3
it's-
minutes, we're going to take a quick 15-minute break, just FYI.
Yep, I think we're probably almost there. So probably, yeah, we should. Now would be a good time to stop and get coffee.
Great.
Next up, we're going to jump into getting the data from spectrograms.
Sounds good.
So
Eric, do you want any help trying to get on Slack so you can see these? I tried sending you a message and like adding you to see if it would maybe send you an email for you to get on, but I wasn't sure if that worked.
I have it in this window. I just couldn't switch to it. I couldn't open it on a different computer.
I got you. Okay, I'm going to show a slide showing that we're on break, so I'm just going to steal the screen share back for a moment.
All right.
All right, everyone, we're going to go ahead and get started again. Feel free to take it back when you're ready, Eric.
All right, let's see. So you should see my screen again,
Yep.
and I didn't change anything, so everything should be visible still. All right, so remember we loaded some MMS data, we loaded some FEEPS data, and some B field data, some ephemeris data. So now that we have so this is the omnidirectional intensity for FEEPS. So now we can actually access the data values. Before we showed how to access the data values for a line plot, but not for a spectrogram. So for a spectrogram, again, it's just get underscore data on the variable that you're interested in. And it, just as before, it returns a named tuple where the first element is just the times, which can also be stored or can be accessed by just saying dot times. And those are the Unix times for UTC. And again, the data values are just dot Y. So you can see the data values. And since this is a spectrogram, you also need the Y values or the Y points for the spectrogram. So those are stored in .v. In this case, it's the energy table. So it's spec.v, and it gives you the energies at each point. And so one thing to note is that if you have T-plot variables that are a function of energy and angle, for instance, distribution functions, the energy and angle tables might be stored as .v1, v2, v3, depending on, so if there are two, it's a function of two variables or a function of two dimensions, it's going to be .v1 and v2, or if it's a function of three, it's going to be, there's going to be a .v3. So one could be energy, one could be theta, one could be phi. So it supports higher dimensional variables. But by default, if you actually want to create a plot, you need to have the .v for a spectrogram. It's not going to know how to plot these higher dimensional variables. So you'll have to load the data in as a higher dimensional variable and then do some processing, like for instance, averaging over angle to actually create an energy spectrogram. But the T-plot model does actually support higher dimensional variables like distribution functions. So moving along a little bit to cluster. So you can load magnetic field data from cluster just by calling pySPEDAS.cluster.fgm. And again, give it the time range, and it goes out and downloads some data. And in this case, we already had the data stored locally, so it just checked that it was current and loaded that file since it was.
We have a quick question, Eric.
Yeah.
Hi, is there a way to, I see that you're downloading cluster from SPDF. Is there a way to download it directly from CSA? Because there are many more data sets available there.
Yes, there is. I don't have an example in here, but there is. So if you go to our repository and then go to the cluster folder, there's a load underscore CSA, and that should have the tools to load it from CSA. And there's a function in there called load CSA.
Cool.
But I actually haven't used this in a while, so if you have problems with it, let me know.
Okay, thanks. And the other thing was, is there a way to download solar orbiter data that's not publicly available, like for MMS?
Not yet.
Okay.
Yeah, right now we're only loading solar orbiter data from SPDF. So we'll have to add, we still have to add support for the ESA servers, which is where the non-public data is going to be.
Cool.
Okay, thank you.
One more question. For spec.v energy points, is it possible to get a range of energies for each channel?
Well, in this case, you'll have to go to the, these are Ben centers. So you'll have to go to the mission team and talk to them about the actual ranges for each channel. So the data products guide, or really the instrument team, is the best place to talk, or the best people to talk to. But the .v, the actual values stored in .v are centers and not ranges. And so we could plot some cluster B field data in GSE coordinates, and thankfully they included the coordinate system in the actual variable name here. So And in this case, we're also increased the X size of the plot and decreased the Y size. So we created a long plot. Just to show how to exercise these X size and Y size keywords a little more. I use these on a pretty regular basis to change the defaults depending on what I'm plotting and how much I'm plotting. And one thing to note is that if you create a small plot with a small time range, you might have the times might actually smush together on your plot. And one quick and easy way to fix that is to just increase the X size and add more room for the labels. And we also have a bunch of other routines for common operations on vector data. For instance, we have routines for calculating dot products and cross products of two different vectors stored in two different variables. So for the dot product, you just import t.p from PySPEDAS. So that's the t tells you that it works on a t-plot variable, and or t tells you it works on t-plot variables. .p means it does the dot product. So you call t.p and give it the first variable and then the second variable. So in this case, we're calculating the dot product of the B field with itself. And it created a new variable with the first variable name and then dot and the second variable name. And we can do the same thing with cross product. It's t cross p from PySPEDAS. And give it the first variable and the second variable. In this case, we're calculating the cross product of the B field with itself. So it should all just be 0. And then we can set some plot metadata by calling options on our new variables. And so we set the Y title for the dot product to B.P. And then we could set the Y title for the cross product to B cross B. And then we can plot the B field, original B field data on top, and then the dot product in the middle, and then the cross product. And we can set the X size and the Y size to actually increase the size of the figure. So now we have the B field on top, the dot product of the B field with itself in the middle, and the cross product on the bottom. Since we did the cross product of a vector with itself, it's just 0 across the board. So you didn't have to use, in this case, it's just one routine or two routines that do the calculations for you. You don't have to worry about extracting the data values and then doing the dot product yourself and then using store data to recreate the variable. It just does all that internally. I think this really highlights the usefulness of the t-plot model, and that you can keep the data and the metadata all together, bundled together, and you can reference it for each product string by string. And there are all these functions that actually just work on them and do the function, do the general routines or internal analysis tools that you actually want to do. So to load some Themis data, it's just PySPEDAS.themis.instrument, and for ephemeris data, it's Themis data is called state. So for it's themis.state for ephemeris data. In this case, we're loading data for probe D and the same time range as before. And you can see it loaded the position, the velocity, as GSE coordinates, GSM coordinates, as well as some spinning coordinate systems. And you can load some Themis magnetic field data. It's just PySPEDAS.themis.fgm. And again, we specify probe D to load the data for probe D and the time range. So it's our time range from March 27th. And you can see it loaded the B field data and a variety of different data rates or data modes. And one thing to note is that if you have questions about what these actually mean, and it's not clear from the metadata, you can always go to the instrument team's data products guides. I know the Themis team explains what all of this is in their data products guides. So I think that's the spinning, this is the low rate mode, the high rate mode, the engineering mode. But all of these, the names of the t-plot variables should be explained in the data products guides. You can load some particle data from the Themis electrostatic analyzer. It's just PySPEDAS.themis.ESA. Again, we're loading probe D. And you can see it went out and loaded the data with the electron and the ions. And so now we can create a plot of some Themis data. We have the B field on top. we have the ion energy flux below that, and then the ion velocity and GSC coordinates, and then the ion density on the bottom. So I'm gonna also show some plasma calculations with Plasma Pi. So for instance, to calculate the upper hybrid frequency, you really, if you're running this in the HelioCloud environment, you actually don't need to do this pip install Plasma Pi. But I included it here since we don't install Plasma Pi by default when you're installing PySPEDAS. So if you want to open this in a different environment like Google Colab or DeepNote, you're going to want to have a pip install Plasma Pi to run the code that's going to follow this. So I just left that in there. And we have to import Plasma Pi once it's installed. And so since a B field data is on a different time scale or different timestamps than the particle data for Themis, you're going to want to, if you're going to do calculations with the B field data and the particle data, you're going to want to interpolate them or one to the other's timestamps. And so we have a useful routine for actually doing that interpolation called tinterpol. So it's you just import tinterpol from PySPEDAS, and you call that function. And the first argument is the data that you want to interpolate, and the second argument is the data that you want to interpolate to. So in this case, we're interpolating the Themis B field B total data, just the B field magnitude, to the timestamps of the density data from ESA. And you can see it created a variable called essentially the same as the first variable's name, and then dash ITRP for interpolated. And now we can get the data and time values as NumPy arrays. So again, just call get data. And notice that we're doing this on the B field, or for the B field, we're doing it on the interpolated data. So we're getting the interpolated B field values. And then the electron density data is just get data and density. And then we can use AstroPy units. Since Plasma Pi uses AstroPy units internally, we can attach the units just by importing AstroPy from importing units from AstroPy. It's just .u or u, and then you can remember the B field data are in .y. So to have the B field NumPy, the B field data stored as a NumPy array with the units attached, you just multiply that B field .y by the units. And same deal with the electron density. NE should have the NumPy data from the electron density multiplied by the 1/centimeters cubed. So now we can use Plasma Pi to calculate the upper hybrid frequency. It's just a matter of passing that B field data and the number density data for electrons to this upper hybrid frequency function in Plasma Pi. And we give it the 2 Hertz option to convert the data to Hertz. And then we can, once that actually does the upper hybrid frequency calculation right here, just this one line, and then we can use store data to create the variable containing the upper hybrid frequency. And again, since the B field and the number density data for the electrons are all in the same timestamp, you could just use B field.times for the times, and then for the Y values, it's just omega upper hybrid. So it's the upper hybrid frequency. And then we can, since we ran store data, we created this variable with the upper hybrid frequency. We can set the Y title, so it's MSD upper hybrid frequency, set the Y subtitle. And this actually includes the units. So we can extract the units directly from the object returned by Plasma Pi. And we could set the Y range, restrict it to 0 to I think 20 kilohertz. And then we can create a plot. So just call it T-plot, and we include the upper hybrid frequency on top, and then the B field magnitude in the middle, and then the electron density on the bottom. And note that this returned units of Hertz, since we told it to convert to Hertz for the output in Hertz. So the units are set to Hertz in the Y subtitle. And so moving along to Van Allen probes, RVSP. So we can load the electric and essentially load the magnetic field data from emphasis, and we can load the electric field data from the EFW instruments. So again, this is the same date, but I'm restricting the time range here to an hour's worth of data in the afternoon. I'm telling it level to load level 3 and to actually do the time clips, so we actually get that 1 hour of data and no more. And again, same thing with EFW data and time clipping. So you can see it went out and loaded the data, did the time clipping, and then we can create a plot. So it's just a matter of plotting. So we're plotting the B field magnitude, the B field vector, and then the E field vector. And so another example with Plasma Pi, you can calculate the ion gyro frequency for this interval. So again, you just return the magnetic field data. In this case, we're doing the magnitude, and we're going to attach the units for the AstroPi. And since those are just in nanotesla, we just multiply by u.nt. And then we can calculate the ion gyro frequency using Plasma Pi. They have a function, plasmapi.formulary.parameters.gyro frequency. You give it the B field data with the units attached, along with P for protons. So that's the ion gyro frequency, and then 2 hertz to return the data in hertz. And so that would be the data in NumPy as or an object that can then be passed to store data to create the variable. So you have omega CI, which is the ion gyro frequency. And then we can, once the variable's been created here, we just call options and give it the Y title until it's the ion gyro frequency, and we know the Y subtitles in hertz, since we said 2 hertz. And then we can plot the B field magnitude along with the ion gyro frequency from RBSP. So historically, this would be a lot of calculations, or a lot of calculations to do a very simple calculation, but really it's got with between Plasma Pi and PyTplot, this is all very simple. I could imagine 100 lines of code just to create these figures, but instead it's just a few. And so you could also load some Arase data. So the thing to note about the Arase data is that I originally wrote this Arase plugin, and then I handed that off to the Arase team, and they've taken over ownership of it. And so the parts that work are all their fault. They're the ones who actually got things to work. The parts that don't work are probably my problem or my fault. So if you run into problems, let me know. But it should work pretty well because they have quite a few people working on it and testing it on their side. So in this example, we're going to load some orbit data, some magnetic field data, some medium energy electron data, and some low energy electron data. And just 4 calls to load orbit data, magnetic field data, medium and low energy electron data. And you just give it the T range and goes out and loads the data from Japan. And what's actually happening behind the scenes is that it's finding that the data was already loaded, and it's just loading the data from locally. And so then once the data variables are loaded, you just call tplot and give it the variable names. So we're going to plot the magnetic field data in asecant and SM coordinates on top, and then the medium energy electrons and the low energy electrons on the bottom, the omnidirectional ones. And just like with MMS FEEPs, these calculations actually occur inside and post-processing once you load the data. So if you just load the data from CDF files, you're not going to get the same data products as if you load it with PySPEDAS, because again, the mission team, the instrument team, the Arase team actually took over ownership of this and contributed the code that does these omnidirectional flux calculations for the different particle instruments. And so one of the newer things that we have is Geopack, a lightweight wrapper around the pure Python Geopack library, which provides SIG and Yugo field models. So you can generate magnetic field models at position vectors using these routines. So we have TT89, TT96, TT01, and then TTS04. So this would be the first T, of course, tells you that it works on T-plot vectors or T-plot variables. The second T is the Siganinko. So it's Siganinko 89, Siganinko 96, Siganinko 01, and this TS is Siganinko Sitnoff 04. And so, for instance, to calculate the T89 model at MMS, Themis, and Arase, since we've already loaded the orbit data for MMS, Themis, and Arase, we can easily generate the field models using T89 at those position variables. The one thing that we have to actually do, though, is to convert the Arase position data. I didn't include a plot of it, but it's in RE instead of kilometers. So we have a routine called TKM2RE that converts kilometers to RE, and it can also go back from RE to kilometers. So you just import TKM to RE from PySPEDAS and then call that on your position vector that's in Earth radii or RE, and then give it the keyword KM equals true, and it goes the opposite direction. And if these data were in kilometers and you wanted to go to RE, then you can call it without this option, and it'll produce the variable in Earth radii instead. And so calling this essentially converts the Arase orbit data, position data, and GSM coordinates from Earth radii to kilometers. And it creates this variable here. And then we imported TT89 from PySPEDAS.geopack and just call it on the position vectors. So this generates the 89 model for MMS at the MMS position vector. This does the Themis D position vector. And finally, the Arase position vector. And then since we loaded the magnetic field, the measured magnetic field data for all three of these spacecraft, we can plot the modeled field along with the measured field. So in this next figure, we plot the MMS modeled or measured field on the very top. So that's the one that's actually measured by the instrument, the FGM instrument. And then below that is the T89 modeled field from the position. And then we have the Themis measured field and the next panel. And then we have the Themis, the modeled field using T89, and the panel after that. You can see if you're looking at the full day, it tends to follow it, at least close to Earth. If you were to zoom in a bit, it would probably not follow it so well. We could also show the ERG measured field and GSM coordinates, and again, the actual T89 modeled field below it. Again, close to Earth, it seems to match. So it seems to be working. And so we can load some twins data as well. So if you want to load the twins Lyman alpha and the ephemeris data, it's pyspedus.twins.lad for the Lyman alpha data and pyspedus.twins.ephemeris for the ephemeris data. And one thing to note here is that we also have the imager data. The main instrument on twins is the energetic neutral atom imagers. And so that's just twins.imager. But we don't have any ways of visualizing or plotting the actual imager data, the energetic neutral atom images at the moment. So I just stuck with some time series, simple time series data on twins for this example. So Lyman alpha and ephemeris. We can create the plot for the two Lyman alpha detectors. Another thing to note is that there are two probes for twins. And so, of course, it accepts a probe keyword to actually allow you to specify the probe. So go to twins in the documentation, you could see there's a probe 1. And there's also, if you want to switch to probe 2, you just say probe equals 2. And so we loaded the Lyman alpha data, loaded the ephemeris data, and then we plot the data. We have the data from the first instrument, Lyman alpha instrument, the second Lyman alpha instrument, and then we have the actual orbit data in GSM coordinates below. And so what if you want to change the size of one of the panels in T-plot? Well, there's an option for that. you just call options on the variable you want to change. You just set panel underscore size. It's measured from 0 to 1. So if you want to make it 25% of what it was, you just put 0.25 instead of 1, and then recreate the same figure. You can see the orbit data panel is now 25% of what it used to be. So this allows you to change the various sizes of panels inside of a T-plot window. So before it was much larger in the Y direction. Now it's 25%. And we also, I think we've shown a lot of examples of how to update options for a single panel. So if you want to set options for the entire figure, you want to use this tplot underscore options function from pytplot. The way to think about this is figure level. Tplot underscore options is figure level options as opposed to panel level options, which just options would do. So for instance, to set the title of your figure, we're going to say twins Lyman alpha data. And then if you want to update the X margin or the Y margin, you can, I think by default, it's around 0.1. So we're decreasing the margin size here in both directions. And then we recreate the same figure. Notice that the margins on this bottom figure are much larger. And it also has the Y title, or not the Y title, the actual title to the figure now. Before it wasn't including that, but we set it. Now it has twins Lyman alpha. And again, notice that it still uses the metadata from the CDF file. So we have the units and the metadata, and then we also have the Y title that shows information about the Lyman alpha detector. So this is the toward instrument, and this is the away instrument. So one thing to note about these global figure attributes or global figure options is that you'll probably want to change these back to defaults if you don't want them to persist for subsequent figures. So if you're going to plot something else other than twins Lyman alpha data, you probably just want to reset the title to empty and reset the X margin and Y margin back to 0.1. I think that's what the default is. And so now we can load some, getting even closer to Earth, and we can look at some POSE data, polar operational environmental satellites data. So it's the instrument is the Space Environment Monitor SIM. So it's just, again, just like before, pySPEDAS.pose.sim, SEM, give it the time range, it goes out, grabs the data. In this case, it's loading the data from SPDF. And I think by default, it set the Y log option to true from the CDF metadata for these energy flux individual telescope energy flux data. So in this case, we changed it to false, to not plot the data on a Y scale, and then we call tplot on the variables. And one thing that I'm showing here that I haven't shown before is the usage of wildcards and a tplot variable name. So if you want to plot two variables that are loaded and you don't want to have to type out the list, you could just use wildcards. For instance, here it tells it to match all these variables that have anything after tel, but before this. So in this case, it's loading all the telescopes. It's loading all the telescope data that match this general form. And so it found 0 and 30 degrees. So if you don't want to, if you have a bunch of variables that you want to create a plot for, you don't want to have to type out the variable name in each case, and they're similar variable names. You can just use this Unix style wildcards to actually match them. So what if you want to change the size of some, increase the size of some of the labels or annotations on the figures? You just use the char size option in pytplot. So you just give it, you call options, give it the variable name, and then the char size, and then the actual value in points. And I think this is flexible. It should accept char size, but it should also accept char size with an underscore. And so in this case, we're changing the size to 16 points. And then we recreate the figure. You can see the X and Y, or the Y title is changed to 16 points. And so the axes font sizes all remain the same. So to change that, that's a global option called tplot_options. You give it the axis font size option. And again, that's in points. So we're changing to 16 points. And then we can call tplot. And this time the axes, we're actually increasing the X size as well. So there's plenty of room for the new times now that they're much larger at 16 points. You can see that the axis font size changed, was increased here. Of course, we can reset the axis font size just by calling that again, tplot options, and giving the axis font size option, and then 12 points. So then subsequent figures, it shouldn't have the axis font size set anymore now that we've reset it back. And so we recently added a plugin that uses the Happy client internally to load some data from the Swarm Happy server. And so this new plugin is just pySPEDAS.swarm, and the magnetic field data, I think, is the only one available at the moment through Happy. So it's just swarm.mag. And one thing to note is the swarm routine should make a good template for missions planning to distribute their data through Happy. And I can show that off a little bit, actually. So to find the swarm, just go to swarm load routine, you go to our repo and go to the swarm folder. And so this is most of what is involved in loading data from a Happy server and PySPEDAS. You just have a general load routine, and then internally, notice that we're importing our Happy load routine, which is just a lightweight wrapper around Bob Weigel's Happy client. Essentially uses Bob Weigel's client to load the data into NumPy arrays, and then we take those data and call store data to actually create the tplot variables from that. So all of this is less than 100 lines of code, or maybe even less than 50 actual lines of code for a simple load routine that loads magnetic field data from a Happy server. And so just like with the other load routines that use CDF data or CDF files, you just call pySPEDAS.swarm.mag, give it the options, and it goes out and loads the data. And right now, this is it's not very efficient. I think it's calling the Happy client over and over again when it really shouldn't be. So there's some performance updates that need to be made in here, but it should work, even if not as performant as it should be. So you see it loaded a bunch of variables, including by default, it's loading swarm A. I think by default, I think it loads swarm A, but we specified it here anyways. But you can also change that to B or C, I think. So in this case, we're going to plot swarm A B field data, and then we're going to use the var label option in pytplot to plot the latitude and the longitude as additional x-axes. So let's see, we plotted the B field data from swarm A, and then the latitude and the longitude are additional x-axes down here at the bottom. So now we are almost to actually getting down to the Earth. We can load some data from the Themis All Sky Imagers. So these are the ASKs. Essentially, this is loading All Sky Imager kilogram data. So it's just pySPEDAS.themis.ask and give it the time range, and it'll go out and load the All Sky kilograms. And we can plot a few of them. And so the ground, we could also load the Themis ground magnetometer data from the Themis ground mag network. It's again just pySPEDAS.themis.gmag. and give it the time range, with the T range keyword. And there are a lot of stations, so it goes out and tries to download them all. And there's keywords to limit which stations you download. I think it's sites. But by default, I just loaded them all. It doesn't take that long to load them all. And so we're just showing the ground mag data at the ATHA, the CHBG, and the INUV stations. And so one useful thing here, you notice that there's large differences between the different components. We have tools for subtracting, like for instance, the average and the median. And so to actually see some interesting stuff here, we can use the subtract underscore median to subtract the median from these t-plot variables. So we just import subtract median from PySPEDAS, and then we call that function on our variable names that we want to subtract the median for. And it created a bunch of new t-plot variables, essentially with the same t-plot variable name, except with -m for the median subtracted. And then we can update the Y range, since the Y range up here is much larger. So we updated the Y range on all of our variables with the median subtracted. We're just going to say -400 to 400 nanotesla, and then call tplot on the variables. And now we have the ground mag data with the median subtracted. We also have data from the magnetic induction coil array network, and these are being released by UNH, so the University of New Hampshire. And to load these data, it's just pySPEDAS.mica, mica.induction. This is the induction coil array data. And you give it the site name and time range, and it just loads the data. And loaded the data in 1 Hertz and 5 Hertz. So we created the plot for the 1 Hertz data. And again, I'm using our wildcards here, Unix style wildcards, to match multiple variables with just one string. So in this case, it's telling it to plot all the spectral variables that match this with one character here. So that would be X and Y. And for the 1 Hertz. And notice that we have the X on top and the Y on the bottom. And so another thing is, since we loaded the kilogram data, and then we also loaded ground mag data from the same station, we can plot those alongside each other. So we can have for this PINA station. So we can create a plot of the kilogram on top and the B field at that station below. And that's actually the B field with the median subtracted. And so I mentioned earlier that you can zoom into time ranges, and it's a lot faster to zoom into time ranges than to do time clipping. So to quickly zoom into a time range, use T-limit from PyTplot. That's limit with a T in the beginning. So you just import T-limit from PyTplot, and then you give it the time range you want to zoom into as an array, start and end. So in this case, we're going to zoom into 3 to 11 on this March 27th day. So it's essentially 3 here to just before. So essentially where the kilogram data exists. So we zoomed in, and once you call T-limit on your time range, you can then call Tplot to recreate the plot with the updated T-limit time range. And this allows you to zoom into time ranges and figures that a lot easier and a lot quicker than you would if you, or at least a lot easier or a lot quicker than you would if you used time clip to time clip the data, especially because in this case, we're only zooming into 2 variables here. But if you apply time clip to, for instance, all of the variables loaded, it would have time clipped every single station, the data for every station. And that would have taken much longer than just calling T-limit to zoom in really quick. One thing that I didn't show earlier is that you can change the Z-axis color bar range just with changing the Z range. Before we used Y range to change the Y-axis range. Z range changes the Z-axis range or the color bar range. So that essentially the only difference between these two is that we increased or decreased the upper limit on the color bar. And then we recreated the figure. So another useful thing is to, I showed pseudo variables earlier, but you could also use pseudo variables to overplot lines and spectrograms. So for instance, we can call store data and create a new variable called overplot. And then we can give it data and then give it a list of variables that we want to combine. So we have the spectrogram variable for the all sky kilogram first, and then we have the medium subtracted ground mag data. So when you combine those, so one way of doing this is to have an array. So you could have, for instance, R1, R2, or you could also do just a string where the variables are separated by a space. So before, I think when I created a pseudo variable, I actually used an array or a list of strings. In this case, I'm just using a string with the variable names separated by a space. And internally, it converts that into a list of strings. And then we set an option on our pseudo variable to tell it to increase to use the right axis. So this tells it to use the right axis and for the second variable. And then we could increase the X margin slightly on the right-hand side. So we're going to use the same X margin as before on the left-hand side, but 0.25. That way we actually have room for the additional X-axis or the additional Y-axis on the right-hand side. And then we just call tplot on the pseudo variable, the overplotted pseudo variable. And you can see.
Question.
Yeah.
Is there any possibility to have milliseconds in T-limit?
Not at the moment. So the downside of T-limit right now is that you have to specify this format exactly, and we need to fix that. Yeah, that's something that needs to be added and fixed because you actually have to do most of our time parsing routines use that fuzzy parsing, but in this case, it has to be exactly this format and does not accept fractional seconds at the moment. But it should soon. It's something that needs to be added very soon.
Great, thanks.
Great. So now when we call tplot on our pseudo variable that combines the spectrogram and the line plot, you can see now we have the spectrogram and the line plot in the same panel along with the right axis. If you didn't turn on the right axis, it'll combine the axes on the left-hand side. And it should honor various options when you do this. So align options, for instance, you could change the thickness of your Gmag or ground mag data with the median subtracted and just so you call options, give it the variable, say the thick option, change it to 3. And I think by default it's 0.5. So this is quite a bit of change. And then recreate the overplot. And it should again, use the line options from the underlying variable. So again, you could change the line style option.
Hey, Eric, can you
yeah.
just scroll a little slower as you're going through?
Sorry, what was that?
Can you just scroll a bit slower as you're going through?
Yeah, sorry.
No worries, thank you.
So you can, just like with thickness, you can set the line style option on a line. In this case, we're changing it to dotted and then call tplot on the variable, the overplot variable. And again, it uses the line style option from the line to dotted. And so one of the more important features that we haven't talked about is being able to actually save the images. So you can save figures now with tplot keywords. So we have save_png that saves a PNG file, save EPS that saves the encapsulated PostScript file, and then save SVG, that's the scalable vector graphics file, and then PDF, saves a PDF file. So to actually save the file, all you have to do is call tplot with your variable names and then that option. So for instance, save PNG creates a figure called overplot.png. sure. Yeah, it should be in here. And you can see it saved the figure. Oops. Yeah, so we created a PNG, a file called overplot.png with that figure. And so, and one big thing is that we can, you now have full control over the figures and the axes, because you can return these objects by using the return plot objects keyword. So, for instance, if we call tplot with the with our variable, so overplot, and then set the return plot objects option to true, it'll return the figure and axes objects. So you can then do whatever you want. These are the matplotlib figure and axes objects, so you can manipulate the figure however you want, external to tplot. And so, for instance, for example, to add some text to a figure, you just you'll need the date time and time zone, and then import matplotlib, so you can use the date to num function. But then you can just use axes. Remember, that's the axes that's returned from tplot. And just type axes.annotate, give it your text and the time where you want it to want the text to show up and the point, and then give it the font size option. It'll actually add text to your figure. See your text down here in the bottom left. I think it's at 10. So on the y-axis, it's 10. And then on the x-axis, it is at 330. So it starts at 330. And so the point of showing this with the returning the figure and axes objects is that you can manipulate the figure however you want. But it's worth pointing out that we very recently added tools for doing this without actually returning, for adding annotations without actually creating figure and axes objects. And I'm going to show an example of that in just a minute. But at the end of this here, I wanted to show that once you zoom in with T-limit, you'll probably want to zoom out at some point. So to zoom out to the full time range, you just do full equals true when you call T-limit, and it should zoom out to whatever. They shouldn't honor the T-limit anymore until you call T-limit again. And so now I want to show some new features. Time. So last month at the PyHC spring meeting hackathon, we created several new examples for pytplot, the matplotlib version of pytplot, and one of those is called annotations. So I suggest going to PyspeDus repository for a top level GitHub page, and then once you're there, you're going to see a list of all of our repositories. Look at PySPEDAS_examples. And then go under PySPEDAS examples, and then notebooks. And so the notebooks that we created last month at the PyHC spring meeting all start with pytplot_. So for instance, annotations. And some of this stuff is going to require the very latest version, which isn't in HelioCloud. That's why I wasn't showing it off. But if you update to the very latest version of pytplot and PySPEDAS, you should have these new features added. So pytplot actually has a function now called annotate. So it's just pytplot.annotate. So you can create a figure, and then, so this shows how to change various annotations with various annotations with tplot options, but then you can use the annotate function. You just give it the text you want to add to the figure and then the location. And by default, it uses fractional figure. So to put it in the middle, it's 0.5. And once you call tplot again, it actually adds the text. And there's options. We tried to pass through all of the options to matplotlib, so you can change like XY chords and tell it to use data chords instead of the fractional figure. And just like in that last example where we used a time, you can use times here if you switch to the coordinate to XY coordinates. You can add text. And you can also set various other options and pass them through as a dictionary. So we're going to use data coordinates with extra large, blue, and make it vertical. So this is the third text. You can see it added the third text. It's blue, vertical, extra large. And you can delete all the annotations just using the delete option. And this is just one of many examples that we have in here now. This would also highlight intervals and vertical bars. This shows off some more new stuff. We have functions called highlight, which actually highlights an interval. We also have a time bar, which draws a vertical bar. So in this case, we're drawing a time bar at 2 seconds. And this time we're drawing a bar at 2 seconds for only one variable. And time bar also accepts other options for setting of metadata like color, for changing the color to blue. So we created a blue bar at 4 seconds. And then this highlight function, this is another one of the new functions that we have in pytplot. It'll highlight an interval for a variable. So in this case, we're calling highlight on the data variable and telling it to highlight between 4.5 and 5 seconds. You can see now when we recreate the figure, we created a highlighted interval between 4.5 and 5 seconds. By default, it's using gray as the background color, but you can change that, the color option. So you go highlight, give it the variable name. Now we're doing it between 5.1 and 6 seconds. We set the color to blue and the hatch to 0 or hatch to O. So it's an O hatch, and then recreate the figure. So now we have 5.1 to 0 seconds. 5.1 to 6 seconds. We have the hatch interval. And then again, just like with annotate, you just set the delete keyword true. It'll delete the highlighted intervals. And just like with those others, you can do the same thing with time bar to delete time bars. And see, I didn't show error bars, but you can also add error bars to tplot variables. I showed how to, so you use the X for the time values and you specify Y for the data values without error bars. But if you want to add error bars, you can have a DY option. So in this case, we create a new tplot variable, data underscore errors, and has the X values of 1 to 6 seconds and Y values of just 1, and then DY of 0.25 at each point. And so that adds the error bars. And then we have a bunch of options to change the error bars. For instance, you can change the option for error every to do every second point. You can change the error bar color with the E color option, change it to blue. You change the thickness of those error bars, the E line width. So we change that to 5. We change the cap size to actually add a cap to 10. So notice that it added caps to the error bars. So we're trying to pass through all of the options we can possibly pass through to matplotlib through options, and just make it as useful and easy as possible. And let's see, another good one is legend options.
Hey, Eric, could you zoom in?
Oh yeah.
It's a little small. Yeah, more.
Let's see. There we go.
That's more doable. Thanks.
So in this case, we created a simple data variable with just values at 1. And then we set the use legend names to actually add the legend. So data at 1. Notice now we have a legend as data at 1. And by default, it uses the matplotlib best option for the location. But we can change this with the legend underscore location option and tplot option. So it's just options, give it the variable and then legend underscore option. And you can, so you can specify a SPEDAS option, which will then move the legend out to the right, like an IDL SPEDAS. And there are a bunch of other options. I suggest just looking at the matplotlib documentation for the available options. We do upper right, upper left, center. So I think in this case we did lower left. So we'll just give it the data and then legend location, lower left, and put it down in the lower left. And then we can switch it back to the best option. And I think in this case, it just puts it back in the upper right.
Hey,
And
Eric,
then
quick
we-
question. Where are you sharing all this from? Is this from the project repo?
Yeah, this is our examples repo.
Okay,
So it's our GitHub page, PySPEDAS/SPEDAS, and then PySPEDAS_examples.
got you. Thank you.
And just like with the other options, we try to pass through all of the options available down to matplotlib. That way, you don't actually have to return the figure and axis options to manipulate anything. We're trying to just make it as easy as possible to just use options to set various options. So for instance, we can change the size of the font to 16 points with the legend size option. I can add a title, the legend title option. So this is our legend. You can increase the size of the legend title size. Notice that the legend title size has been increased to 20 points. You change the color of the text in the legend, change it to blue here. If you have multiple items in the legend and you only give it a single string, it'll change each one to blue. But if you can also, if you have multiple items in the legend, you can give it an array of items and change the color of each one. You can add a shadow to the legend. So it's just turning on the legend _ shadow option. You can see it add the shadow. Switch the marker in the legend to the left-hand side instead of the right-hand side. Remember before it was on the line was actually on the right-hand side. But you can switch this around with the legend marker first option to set that to true. You can turn on markers like symbols and then increase the scale of the marker inside the legend. So that's like hexagons at every data point. And then of course it includes the marker in the legend. Decrease the marker scale, change the background color. It's called the face color. So it's just legend _ face color. You could change the edge color. So in this case, we're turning it to blue. So we have a pink background with the blue edge. And just like before, we can move the axis. So we can change the legend location to the SPEDAS option, and it moves it out to the middle of the right, just like an ideal SPEDAS. And of course, we can't go through all of these today, but there's more in this repository. So it's just PySPEDAS _examples, and then dig down to the notebooks folder. We have examples of loading data from the happy servers and some coordinate transformations. I think we pretty much showed how to do that in the notebook, how to change various spectrogram options. So that shows things like interpolation and spectrograms, automatic interpolation. We have more on markers and symbols, turning off the lines between the markers and the symbols. So there's a bunch of examples in here. I suggest if you're interested in pytplot stuff, this is probably the best place to go for examples of pytplot. And one other very, very useful thing is the MMS-examples repository. So I think there's at least 20, probably more than 30 notebooks, at least 20. So there's a basic folder and an advanced folder, and we're trying to follow the same naming scheme as IDL, our notebooks and examples in our IDL. So basic shows things like very basic things like loading the data, adding error bars to the FBI data, doing orbit plots. This is a new one with quaternion coordinate transformations using SpacePy. So it's all just very basic stuff. And then we also have an advanced folder, which is more advanced stuff like generating spectrograms and moments from the distribution data directly. So if you're interested in MMS stuff or more advanced calculations, take a look at the MMS-examples folder. So for instance, in this case, we show how to calculate spectrograms and moments from the FPI distribution functions, as opposed to just loading the moments from the MMS files, CDF files. And when we have element coordinate transformations, We have the basic dayside and tail science notebooks that reproduce the scientist in the loop figures for the dayside and tail science intervals. And we have a bunch of plasma calculations with Plasma Pi for MMS. I showed how to use Plasma Pi for Themis and RBSP calculations, but we have a bunch more here for MMS. I think by default, let's see. Yeah, so we calculate the alphane speed, plasma beta, ion inertial length, bi-length, ion gyro frequency, gyro radius, lower hybrid frequency, upper hybrid frequency. And then we create t-plot variables and plot those variables. And another useful thing that's it's more general than MMS, but calculating wave polarization. We have general routines for doing wave polarization calculations. And this example just uses MMS SCM data, but it should work with any other search coil data as well. And essentially shows how to do all the same wave polarization calculations that we do in IDL SPEDAS with PySPEDAS. It actually generates the same figure. And let's see one other thing. I think we missed the dynamic power spectra somewhere. Yeah, I think the SCM notebook also has examples of doing dynamic power spectra in the basic folder. So it shows how to do the dynamic power spectra, I think. Yeah. So you can see there's a wave information there, calculating the dynamic power spectra. And there's also the curlometer technique. We have routines for MMS for actually calculating curlometer, doing curlometer calculations. So that interests you, we have notebooks for that as well. So if you're interested in various analysis tools, MMS examples should have a lot of examples, especially if it's on MMS data. But a lot of these generic tools are also, or a lot of these tools are generic enough to be used for other missions and instruments as well. And I think that's all I have. Is there a line of questions that I missed?
Awesome. First, thanks, Eric. Awesome. There is one question in the chat. Is there a way to calculate 1D or 2D velocity distributions from the particle distribution functions?
So is that to plot the 1D?
They just said calculate.
Not yet. I'm working on that. It's in development.
Awesome.
It is coming though.
Great. Any other questions from the room? If not, we can go ahead and wrap up. Thanks, Eric.
Yep.
All right, everyone, same time, same place tomorrow. See you then for the last day.